mature, so like any. And there. All right. Well, thanks so much to the organizer for putting the paper on the program. This is joint work with Regis, Amy, and John, who are all here. So let me dive right in. Thank you. So the objective of this paper is to compute impulse responses of some shock epsilon t on some outcome variable wt plus h. At the moment, there are two prominent methods that people are using for this. One is to use a VAR. This has the advantage that it typically gives you a low variance, but we have some worry about dynamic misspecification, which then lead to some bias and subsequently maybe some coverage distortions. The other approach is to use a local projection, like a direct regression of the outcome on the shock. And that gives us typically a low bias, but we're worried about a high variance. So the question that we pose in this project is, what are reasonable ways to avoid this trade-off and get the ambitious goal of having low bias, low variance, which will obviously have to pay some form of a price for it, but let's see what we can do there. Okay, so the project has two key ideas, which are a little bit distinct in their approach. The first is, let's do some quote unquote appropriate model selection. The idea is pretty simple. Like, we know that if we pick a var with a very large lag length, the impulse response of the var is going to be pretty similar to the one from the local projection. In some DGPs, that's going to be the best we can do because otherwise we encounter more bias. But in other DGPs that are more favorable to the var setting, we might be able to reduce the lag length and get a smaller VAR, which has still a low bias, but improves the variance. So what we do in this project is we view the var as an approximating statistical model for modeling the exact impulse response that we care about. So we view the var just simply as a tool, a power tool, if you will, to approximate the IRF that you care about. And with that objective in mind, we then choose the best VAR for estimating the impulse response of interest. So directly target the variables, the lag length, such that you get the best impulse response estimate for your purpose. I'll show you this idea in 2 slides. It's very straightforward. Let me remind you of the procedure of forecast cross-validation. Okay, so this is also, think about it as model selection using out-of-sample forecasting. What do you do in this scenario? You have your set of candidate VAR models, all defined in terms of variables and lag lengths. You take a candidate VAR, you estimate it up to some horizon t, and produce a forecast. H periods ahead, say. Subsequently, you compare that forecast with the realization at time t plus h, and you repeat that several times over some out-of-sample period, and then you just pick the var that would have performed best in terms of having a low bias, perhaps, or in terms of a mean squared error. One thing that's nice about this procedure is that it's very specific to the object that you're interested in. You can pick the variable you care about, you pick the horizon, and you can pick the metric that you care about, bias, mean squared error. The only problem with it in this form is that it's targeting a forecast. And we just said that whole project is about impulse response estimation. So how can we move from one to the other? The only insight that you need for that is to realize that what is an impulse response? Well, that's just a forecast, but projected on some shock of interest. So what we're going to do now is we're going to take this here, what's on the left-hand side, we're going to project it effectively on the shock of interest, and then you will see that we can get to something that we call conditional cross-validation, which is essentially going to be targeting the impulse response that we care about. The route is exactly the same. Estimate the candidate VAR model, construct your impulse response using the data up to time t, and now not compare with the realization, compare with the realization times some measure of the shock that you care about, okay? Subsequently, you repeat this again over a variety of validation periods, say, and you pick the VAR that gives you the smallest average bias, impulse response bias, or the smallest mean squared error that you would care about, okay? So intuitively, why does it work? Well, the expected value of the realization times the shock, that's just a noisy proxy, but unbiased, for the impulse response that you care about. So when I repeat this sort of experiment several times, then we can get an accurate estimate for either the bias or the mean squared error that we care about. Okay. So what do we show formally? We show that if the true data generating process is a vector moving average model with infinite length, then as the validation sample increases, conditional cross-validation criteria, either targeting bias or mean squared error, is going to be consistent for its counterpart. This does require the validation sample, obviously, to go to infinity, so you need to have some out-of-sample period, but then you can consistently approximate exactly the criteria that you care about, the bias of the impulse response or the mean squared error of the impulse response. Okay, we show an additional result as well. If the DGP is a vector moving average model, but now has some local to zero coefficients, so it's kind of difficult to distinguish between the two, we show that this conditional cross-validation criteria is going to be asymptotically unbiased estimate for the population quantity that you care about. And hence you lose consistency, but at least you still have an unbiased estimate of the object that you care about. And this also holds when the validation sample goes to infinity. Okay, so that was in 2 slides, the first idea in this project. The second idea is somewhat different. The second idea in this project is based on the view that there is more to the world than local projections and VARs. Specifically, we can think about alternative impulse response estimators that, on the one hand, retain the computational ease of the VAR and the local projection, but still generalize or lie in the space between the two to get the benefits from both sides. So low bias and low variance. And obviously there's a price we're going to pay for that, and I'll be clear on that. But in a nutshell, the idea is as follows. A local projection computes a direct regression of the outcome on the shock h periods ahead. A structural VAR computes a direct effect for horizon 0, an impact effect, and subsequently propagates that forward using a predictive model, the VAR recursions in this case. So when you look at these, the way written down here, what's the middle ground in between here? That's estimate direct effects up to horizon S, where S is somewhere between impact and horizon H, and subsequently propagate these impact effects forward using some forecasting model, not necessarily a VAR, could be just simply a direct regression by which you're going to propagate that forward. That's one way of viewing the middle ground between local projections and VARs, and today's talk is going to focus on this sort of second idea. And in order to explain that in detail and provide motivation and the formal results, I'm going to be taking a slight detour and explain you where this name surrogacy-based estimators comes from. And for that, we need to make a little bit of a detour through the medical literature, which we're going to do in 3 slides, and then we'll get back to our time series setting. So let me just explain you what the key idea is here. Okay. Good. All right, here we go. So in the medical literature, or in cross-sectional designs in general, people face the following problem. You want to know the effect of a treatment on some long-run outcome, here still called W, but the long-run outcome is not observed in your experimental data set. Think about some sort of a drug trial and you want to know like later life health outcomes, but you know you can wait, but that's typically not feasible. So what do people do in this literature? They use the idea of surrogacy. Let's look at some short-run outcomes, which I will call Y here, the surrogates. And the idea is that these surrogates are going to capture all the treatment relevant information for our long run outcome. The DAG below there explains it clearly. You have a treatment that affects the long run outcome, but all the effects go through the surrogate variables, okay? So in this literature, then it opens up the opportunity where you use your treatment sample to estimate the first error, like the effect of the treatment on the surrogates, and then you can use some other data set to figure out how do the surrogates propagate further to long-run outcomes. That's sort of the mechanism that they have in mind there. So let me give you just one example. Suppose that you have treatment is HIV therapy, and the outcome that you care about is progression to AIDS or death years later. Surrogates that they use in this literature are the viral load. The viral load can actually be measured several weeks after the treatment is administered. And the idea is that that contains all information that you need for predicting the longer run outcomes here, the progression of the disease. So to put it slightly more formally, the mechanism is that, the main idea is that all mechanisms, like the treatment happens, and then lots of stuff happens, but all these mechanisms' latent states essentially can be measured through the viral load, okay? And then once you know this viral load, after a few weeks, that's sufficient to get your long-run outcome. That's the idea that they use. Put a little bit of math on that. The surrogacy assumption, as we can state it here, is that the projection of the outcome on the surrogates of the shock and the shocks is equivalent to the projection of the outcome on the surrogates alone. That means that once I know the surrogates, the shock provides no further information on the outcome that I care about, okay? So what's the implication of this? Well, that means that the impulse response or causal effect, if you will, of the treatment on the outcome can be decomposed as a product estimator, which is tau times beta, tau being the short-run causal effect, the effect of the treatment on the surrogates, multiplied by a long-run predictive effect, which is just a prediction of the surrogates on the outcome. So you get this product estimator here, okay? So that's the main idea of surrogacy as it is used in cross sections. So here you have to imagine that I have multiple treated units, I have multiple surrogates, cross-sectional design, and then I can estimate these things using regression. Okay, so we're going to take this idea and we're going to move it to a time series setting, and we're going to try to exploit that to improve our impulse response estimates. That's the key of the paper. Okay, so the first thing we need to acknowledge is that in time series, the long run outcome is usually observed. So I don't, it's observed. I don't face this problem of needing two data sets. Okay. At the same time, as we started off this talk with, impulse responses are difficult to estimate accurately, especially at longer horizons. VARs can be prone to bias, local projections can be not efficient. So we said that. Okay, so the idea is to exploit these surrogates to improve the efficiency of impulse response estimate without incurring, hopefully, a bias cost. Okay, so to sort of get to this objective, I'll show you two things on these slides. First, how surrogacy arises in your conventional time series models, right? So first want to establish that surrogates actually can exist in our time series world. And then subsequently we'll build estimators based on that idea that exploit the surrogacy assumption. Okay, good. So let me start you off on that with a simple example. Simple example is going to be an ARMA 1-1 with IID shocks. The impulse response impact effect is normalized to 1 in the first horizon, and the rest of the impulse response, Okay, so this is going to be our leading example in which we explain everything. I'm going to take, before I go to this exact example, I'm going to put B is equal to 0. So I'm actually going to look at an AR1 for total simplicity. In an AR1, things are very simple because the surrogacy assumption holds exactly, and it allows me to focus on the efficiency gains that you get from this assumption. Okay, so let's go there first. So put B is equal to 0. Then with IID shocks, it's very simple to see that any realized outcome between time t and time t plus h is a valid surrogate. So for example, I put S, the surrogacy horizon, to 0. Then I have that once I know the realization WT, the shock no longer has any effect on the outcome variable h periods ahead. That's very straightforward. So in this particular model, surrogacy holds exactly, and we can decompose the impulse response into theta naught, the short run impact effect, times beta h, which is just the propagation of the shock, which is here, since it's an AR1 model, is just rho to the power h. So you recognize there the AR1 impulse response. Great. So why would you want to do this, right? Like, why do you want to go this route? So that's here, okay? The main reason is going to be the following. Relative to a local projection, a surrogacy estimator is going to be efficient usually in a different part of the parameter space. Specifically, surrogacy estimators are going to be useful when persistence is very high and the surrogates are going to be good predictors for the long run outcome variable. When persistence is not so high, well, then a direct local projection is going to do better. So it makes sense to combine these two estimators to sort of get the best of over the entire parameters, so the best of both. Okay, so that's written here. Local projection just projects the H period ahead outcome on the shock. A direct surrogacy estimator would do the following: take the impact local projection impulse response, theta naught LP, multiply that by some prediction coefficient. I'm not going to cheat here and use the fact that I know that it's an AR1. So I'm just going to run a direct regression of WT plus H on WT, and I'm going to multiply those with each other. These two estimators are efficient in different parts of the parameter space, and that just motivates taking a linear combination of them. Intuitively, now you have two moment conditions, you can construct a GMM estimator, and it's going to give you more efficiency. Let me show you that just in a bit of a picture. So this is the asymptotic variance ratio of local projection estimator against this direct surrogacy estimator. What you see here, the blue area, this is where the surrogacy estimator is more efficient. In the red area, the local projection is going to be more efficient. This is the asymptotic variance ratio. So you see that if persistence is high, the rho on the y-axis is high, then the surrogacy estimator outperforms the local projection. And if persistence is low, it does not. And you can just see that here from the regression, right? When persistence is high, then WT is a good predictor for WT plus H, and it has a small variance typically. So then you can win and otherwise not. In general, I don't want to win or lose, so I'm just going to combine the two since both are valid estimators in this example. So that motivates the linear combination of the two, which will do always better. That would be just a blue picture here relative to local projections, but that's not that interesting to show you. Okay, this brings us sort of to a general class of surrogacy estimators. What are you going to do? You're going to, up to horizon S, your surrogacy horizon, I picked S as 0 as an example, but in general, it's up to horizon S. You're just going to do local projections. You're going to compute direct causal effects. Subsequently, you're going to propagate those direct causal effects forward using some forecasting model. So on the second line, you see the surrogacy estimator, which is a weighted combination of the local projection estimator and the surrogacy estimator, where the surrogacy estimator is just the impact effects times the prediction coefficients. And then when there's various versions possible, because you have a lot of freedom now to choose the forecasting model that you like the best. So if I use a direct regression, I'm going to refer to this linear combination estimator as a surrogate local projection because it's like two direct regressions. If I want to do propagation forecasting using a VAR, so beta is modeled by a VAR recursion, now then I'm going to call it a surrogate VAR estimator. But you can go on here naturally, right? Maybe these are not even the best forecasting models that you want to consider. Maybe there's a whole array of factor models, etc., that you want to be considering for propagating these impact effects forward. With good surrogates, we have that the asymptotic variance of the surrogacy estimate is going to be much smaller than the asymptotic variance of the local projection estimator. This obviously requires the surrogates to be valid, and that they have to be informative about the long-run forecasts. Okay, so let's move on now. So that's an AR1 case. That's a little bit, too stylized, perhaps. Let's move on. Yes.
Sorry, just a
Absolutely.
quick question.
Yeah.
On your previous slide, I'm just sitting there because the efficiency depends on the rho, right? The persistency parameter.
Yeah.
The rho. So why don't you make the combination weights depend on H? And
yeah.
how are you going to estimate that?
Sorry.
In principle, you could have for lots of different overlapping values of H, right? Little H, and then you could estimate it almost from that.
Yeah.
Or you could sort of like a pooled, estimation procedure, or you could estimate it for each H because it sort of depends on, the cumulative effect of this persistency, right? Parameter, how close it is to one.
Apologies, it's a typo.
Oh,
It should
so
be
you just-
it should be W hat H. I just simplified the notation to
Yeah.
keep it at bare minimum. But yeah, I fully agree with you. The asymptotically efficient weights are horizon specific when you calculate them here. So all my statements pertain to that. And then you can choose indeed whether you want to do the local projection jointly or whether you want to do it like horizon by horizon, like uniform. Thank you. Thank you. Sorry. Yeah, that's my bad typo. Good. Let's move to ARMA 1.1. Okay, ARMA 1.1 I think is an important example because it is going to capture like sort of simplify VARMA PQ, which we think about as being sort of the solution of DSG models, etc., etc. Okay, the first thing to note is that in an ARMA 1.1, exact surrogacy is going to fail for any finite horizon S. This is very intuitive because just think about like in an invertible ARMA, the shock can only be written as an infinite linear combination of the observables. Hence, in this model, the moving average term at time t-1 is a latent omitted state. If I want to capture that, hence, I need infinitely many observables. Okay, so surrogacy, the intuition is that the moving average term only gradually gets revealed by the observables. So what we do is we're going to define an approximate surrogacy condition. Specifically, there's now going to be a deviation between the projection that includes the shock and the projection that excludes the shock. That's going to be denoted by psi THS. And we can show that some norm of this mistake in the exact surrogacy condition is going to be bounded by the term on the right-hand side there. The important thing to observe is that this deviation in an invertible ARMA is going to shrink geometrically. So when S becomes larger and larger and larger, this is going to go to zero. This implies that true impulse response is going to be equal to this product plus a small bias term. Okay, so that's what happens in an ARMA 1.1. How are we going to try to operationalize this in practice? Like what is small in this setting? So we're going to do this with sort of making it the coefficient. Yeah, sorry.
Sorry to interrupt.
No.
So is it going to be important that also later on, whenever S is large, this thing is going to shrink to zero? Because I guess in a non-invertible setting, it would not, right?
Exactly. So we're going to exactly have that. We're going to want to increase the information set in this case. So you want to add variables. It's literally the same as sort of like thinking about invertibility, but then with future variables.
And is it going to be then the case that within the overall set of variables that you're going to be adding, is something that is going to be
exactly. It's going to be like a vanishing fraction of the sample size. That's a theoretical construct we did put on it, but it's really just invertibility, but with future variables that I can span it. Yeah, perfect, thanks. So yeah, this is how we did it in the theoretical framework. Psi t is going to be a vanishing fraction of the sample size, so it's going to decay to zero with some rate t to the minus a, where a is going to be essentially making everything negligible, so greater than a half. This construct was sort of motivated by the sequence of papers that models moving average terms using local to zero coefficients, and it's just a way for us to formulate this. So here you see in ARMA 1.1 with a local to zero moving average coefficients. In this scenario, our approximate surrogacy condition is going to be satisfied when S is greater than or equal to 1. So the surrogates will be time period, the time t realization and the time t+1 realization. Once I've controlled for that, everything else is sort of vanishing away. And you can feel from this that it's going to be very, very important that we do quote unquote conservative surrogacy selection, right? We want to be like on the safe side, not to incur this bias, but said that for the longer impulse response horizons, we still are able to reduce the variance. And I'm going to show you how we do that, obviously. Okay, so here's just one example with some pictures. You see on the bottom left, there's the bias picture. You see that the bias is high if the moving average term is high. The variance here is always blue because it's a highly persistent design, and the mean squared error has this top red corner where the bias dominates the variance. And then remember that this is again the comparison between a local projection and the direct surrogacy estimator, not the weighted average of the two. It's just for clarity of the picture. It explains when these estimators are doing well. Okay, so good. 2 slides on putting things in perspective. First, there are many estimators that we already know are special cases of surrogacy estimator. First of all, local projection. Obviously, if I choose the surrogacy horizon past the last impulse horizon that I care about, then exactly surrogacy is just the surrogacy impulse response function is just the local projection impulse response function because S is sufficiently far away. So that's one default case. The second default case is to realize that a structural VAR impulse response is also a special case of a surrogacy estimator. Here I show you the impulse response of a structural VAR, which you all know. What is it? Well, it's the jth column of the impact matrix, which is just your impact effects, theta naught, times the ith row of the propagation of the companion form matrix of the var to the power h. So that's your predictive model, your forecasting models. So you can view our surrogacy estimators as a generalization of structural VARs where impact effects are computed for S+1 horizons instead of 1 horizon, and impact effects are propagated in different ways. Not necessarily a VAR, but we can do direct regression, etc., etc.
So this dichotomy, how do you think about internal VARs fitting in? With say given, so say you have P lags in there, then you're still up until that you're going to be kind of directly projecting on the shock, and afterwards, I guess then there would be kind of the surrogates from that horizon onwards would be the kind of like shock itself there, but without kind of propagating that forward, and then the other observables. So that would be also somewhat in between those two. Right?
Sure. But it relies then within the VAR structure.
Yes.
Exactly. So this is like saying, let's take the outer view, right? So I agree that there's sort of an analogy between lag length choice and selection of S, right? That's what you're kind of like sort of hinting towards, the set of surrogates that you choose. And then, I can get away from the VAR entirely by just propagating using direct regression. Okay. Second thing, to just put things a little bit in perspective, is that when we do inference in a structural VAR, we require no serial correlation assumption in order to get correct unbiased impulse response estimates. It's useful to observe that no serial correlation is stronger than a surrogacy condition. In that sense, in that way, surrogacy generalizes the structural VAR, and it doesn't do that by imposing additional assumptions. No, it relaxes the structural VAR assumption, and the intuition is pretty straightforward. And surrogacy only is a condition on one single shock, right? Whereas no serial correlation is a condition on this entire vector of shocks. So that's one. Second, no serial correlation, you can think about that for all variables, the other variables and their lags, etc., act as the surrogates. Whereas here you can select any particular set of surrogacy. So I have a small proposition, but this is pretty straightforward. You take a var. Suppose that the shock of interest is a component of the error term UT here, then the covariance, this no serial correlation assumption, implies the surrogacy assumption, but the converse is not true simply because we're talking about one simple shock. Okay, so that's just reassuring. We're not increasing assumptions in this particular sense relative to a VAR. Okay, so let me talk about the general framework a little bit. The only thing I want to do now is just tell you the formal assumptions, and then bringing this into a general framework, GMM, such that you can, fill in the theory using the general GMM framework. Okay, so that's all I want to achieve here. Okay, approximate surrogacy is stated as follows. There's 2 differences here compared to my simple example. First, y t to t plus s, you have a variable choice in there. You can choose different types of variables. It's not confined to using only the variables in the ARMA, right? You can pick whichever set of surrogates you want. Second, I included some control variables, which is all not that exciting. And the same approximate condition holds, is that this is going to be a vanishing fraction of the hold up to a vanishing fraction of the sample size. Okay, this is somewhat very analogous, I wanted to say that, to like a Granger non-causality assumption, right? That these we're much more familiar with in terms of worthing. It's like the shock has approximately no further predictive effect once you account for the surrogates. That's how I think about it. Okay, so if this surrogate impulse response surrogacy holds, then the surrogate impulse response decomposition becomes as follows. Impulse response is the product of the short-term causal effects, which are here denoted by tau, because we now have y, and they're not like the same as the outcome variables anymore. So I denote by tau 0 to s, the short-run causal effects of the shock on the surrogates, times the predictive effects, the betas, and those are just the coefficients from that linear projection that we have there. Okay, good. Good. We can view all the surrogate estimators simply as constraint GMM estimators, which is kind of convenient because it provides us with a general way of looking at this. I'm going to write it out here for surrogate local projection, so where you run a direct regression for propagating the short-run causal effects forward. I'll leave the surrogate var for the paper. Good. So the approximate moment conditions for surrogate LP, there are three of them. The first one is the conventional local projection moment condition. The second one is the moment condition for your short-run causal effects. The third one is the moment condition for your predictive regression. And this is then subjected to the constraint that the impulse response is equal to this product of the two. Okay, so that's the surrogacy assumption imposed as a constraint here. This means you can show that the efficient GMM estimator is then going to be first order equivalent to this linear weighted average of the two. So that makes it easier to implement in practice. You don't need to do the numerical optimization if you have to do a big simulation, as I will have to do in a second. Then we're going to show that we can show that surrogate var works similarly. All right. Good. So this is a very important topic now. How are we going to select these surrogates? Okay. Candidate surrogates are essentially indexed by two things. Well, we index them by two things, which is choosing the variables themselves, which is n, and choosing the surrogacy horizon s. Okay, so that's our surrogacy selection problem. And you can formulate it in the following way. For each candidate set of surrogates, ask whether the shock still predicts the future outcomes after conditioning on the surrogate state. Okay, so valid surrogacy would mean that gamma h is equal to 0 for all post-surrogacy horizons, so for all horizons after s. Okay, so this is just what we found in simulation. Under selecting S is costly. Okay, that is costly. Why? Because the remaining misspecification bias that you make gets propagated through the entire impulse response. So that's something we really want to avoid. Over selecting S is usually less costly. Yes, you're gonna pay some price in terms of having a lower, higher variance relative to making S small, but at least your bias is controlled, and overall that's going to give a much nicer picture, as I will show you. So in the paper, we explore different conservative selection criteria. We have different ways of doing it that we're thinking about, and I'll just share one of them with you and mention a few others. The first one is pick the surrogates such that with high probability, the forecasting gain from including the shock is small. So what do? You compute the relative forecasting gain, RH, from including or excluding the surrogate, and then you essentially build a confidence band for that, and you're going to maximize the confidence band over all the post-S criteria. And then in our current implementation, we choose the smallest candidate for which this bias is small. The important thing, I guess, here to note is that we take into account the uncertainty in the relative MSC estimate. That's what makes the procedure sort of conservative, because we're going to say, well, if there's some uncertainty on whether these are valid surrogates, then we're not going to use them up to some bound, obviously. But there's many other approaches that you can consider here: selection based on coefficient estimate, t-statistic, etc., screening based on information criteria. There are various things that we can consider here. So let me show you now some simulation evidence to sort of highlight how this works in hopefully realistic designs. So the main question of the simulation study is that, does introducing this additional surrogacy-based moment condition improve the variance without adding too much bias to the design? I'm going to look at two different environments. The first is a stylized 5-variable Varma 3-2. And there I'm just going to fix S at different possibilities to show you the consequences of getting S right or wrong and show you the variance gains that you get from that. In the second, I'm going to turn to, well, paper that Christian had, like where they do a very empirically realistic dynamic factor model. I'm going to try to see how the surrogacy estimators fare in that model. And it's important to know that exact surrogacy never holds in any of these designs. And we will be comparing local projections, VAR, where you select the lag length using AIC, surrogate LP, and later surrogate VAR. Okay, so I've summarized it, the simulation outcomes in the following. You're going to see a sequence of outcomes for SS1, SS3, and SS6. Okay, the surrogates here are just the variables in the Varma. I just include all of them. Okay. So on the left, you see the true impulse response. The middle column is the absolute average bias. So every row, is a different simulation design with a different impulse response, a different Varma model. The true IRF, the absolute average bias, and the variance. Okay, so what do you see here? Well, the first couple of simple things to see, the VAR has a relatively high bias, but it has a very low variance. Local projection has a low bias, but a high variance in this design. So that's the purple and the blue lines. The important one for us is the red line. And you see that when S is 1, so the surrogacy horizon is 1, but my DGP is a Varma 3-2, so S is way too small. You see that we have the same problem essentially as a VAR, right? It's just a VAR in this case. So we're like being very erratic in our bias. Sometimes we get big biases. Sometimes we get, this is for surrogate LP, by the way. Sometimes we get big biases and it moves all over the place. Okay, so clearly S equal to 1 is not the right thing to do here. So let's increase S a bit and see how this improves. This is for S is equal to 3. And you see that our bias is now nearly on top of the bias of the local projection estimator. So it's very, very close to that already with S is equal to 3. Nonetheless, when you look on the right-hand side, which is the variance reduction picture, you see that the red line is below the blue line, which means that the surrogate LP estimator has reduced the variance. This variance reduction here is around 10 to 30%, depending on the DGP, right? So it depends on like how persistent the actual VAR is, how much gains you will be able to get. One other nice thing is that when I make S is equal to 6, you see that the bias is just the same between the local projection and the surrogate LP estimator. Okay, they just have the same bias, but the variance is, well, substantially reduced, if you will, depending again on exactly which data generating process we look at. All right. Yes.
But for SE1, you showed that the bias was even lower for the surrogate than for the LPs.
It can happen. It can happen, but if you look across a variety of DGPs, then you will. Well, this is just showing you different Varmas, where in some you have, like, look at all the impulse responses are vastly different here. For some, the VAR will provide a better approximation than the local projection in general. For some, a surrogate LP, which was direct times direct, does a better approximation. It's just all over the place. That's how I at least interpret this, right? It's just anything can happen here. I can have a higher bias, a lower bias, but there's nothing sensible to say about it because it depends purely on the DGP. What I care about is that regardless of the DGP, I can sort of have a bit of a bias control, at least if I pick S large enough. Okay, yes. Okay, so here I fixed S. Okay, now as we talked about, like we need to select S in practice, which means that, you know, we're gonna make a mistake sometimes. So we're now gonna move to this large dynamic, oh, sorry, let me first wrap this up. LP low bias, but high variance at long horizons. VAR ASC can reduce the variance, but large bias cost. Surrogate LP estimators behave surrogate estimator behave like LP if S is large enough, and you get a nice variance reduction on top of that. Very good. So moving to the dynamic factor model design. So I just literally replicate what they do, and I insert the surrogate estimators. I now consider surrogate LP and surrogate VAR. What's important is that now I need to select the lag length. So I'm following their approach by picking the surrogate variables at random and only selecting S. The reason for doing that is purely computational, has nothing to do about my willingness to do more better surrogate selection, but it's just a huge DGP. So this is going to be sort of a lower bound on what is possible. But even here you see that the bias of the surrogate LP estimator is quite close to the local projection estimator. It has at least a much lower bias than the VAR. And we still get a neat variance gain, especially at the longer horizons. So selecting S conservatively, this is the variance gain, selecting S conservatively, yes, it hurts you a bit, but you still get a nice variance reduction, especially after the surrogacy horizon. And you see that this is a very persistent DGP with high persistence. So S is picked very, very large here. Okay.
So that's a non-stationary DGP, right? From what you, it probably looks even better in the stationary.
Yes, it does. It does. I picked this one on purpose because no, that's right. That's right. Okay. So word of caution, like selecting S is important. It means also that you can make mistakes if you get S too small. So you need to ensure that S is large enough. And if you don't have that, you get a mild medium bias. So you still get variance gains. Here, the variance gains of the surrogate LP and surrogate VAR are sort of comparable to each other. What's to do for our project here is at the moment, the surrogates are selected at random from this dynamic factor model. That makes them a little bit, that's a very poor choice in general to do that. So we need to improve a little bit on that. We're only selecting S here, and then hopefully we will be able to sort of reduce the variance more substantially. Okay, so I'm going to conclude. Surrogacy, as we introduced it, provides a middle ground between local projections and VARs. The key assumption that you make is kind of an informational invertibility type assumption. After you condition on the short-run outcomes, the shock has little remaining predictive content for the future outcomes that you care about. The resulting estimators are simply combinations of short-run causal effects with predictive propagation, and you can frame this as a GMM problem, so the standard methodology applies. And simulations suggest that without incurring too much misspecification, you improve without introducing too much bias. Okay, I will leave it at that. Thanks.
We have time for a quick question. Well, we can just go on to the next page.
Okay, so that looks like it clicks. Should I just start straight away? Okay. Great. Well, thank you very much for putting the paper on the program, and to all of you for coming. Very happy to present this joint work with Ed Manuel, who's a fantastic grad student at the LSE, on identifying policy causal effects from rule changes. Okay, so one slide, kind of quick overview of what we try to do in this paper, and let me maybe try to remove this thing. Okay, can I still then click? Yes, I can. Very good. Okay, so a common objective of empirical business cycle macro is that we'd like to figure out how policy, monetary policy, fiscal policy transmits. And methodologically, the usual strategy we follow is we try to somehow identify what we're willing to call kind of a structural policy shock, and then we regress on that using a local projection, using a VAR, or using some kind of hybrid technique along the lines we just heard about. Okay, there's a kind of somewhat more recent alternative. There's a kind of a bunch of papers that try to do something broadly, and I'll obviously be a lot more specific as I go along, broadly along the following lines, where you have some outcome of interest, say future GDP, inflation, and so on, and you regress this on some kind of usually non-policy macro shock. So for concreteness, suppose, say, an oil price disturbance. And then you ask in this kind of broadly diff and diff style intuition of how the propagation of this shock changes as some measure of systematic policy changes over time. So Emmy John, together with Masao Fukui, have a paper that does something kind of like that in a cross-section of countries, seeing how changes in exchange rates propagate across floating and pegging countries. Over in the time series, there are papers that say, look at time-varying conduct of US monetary policy, depending on the composition of the FOMC, and then ask how, say, an oil price disturbance propagate. Okay. What we want to basically ask in this paper is kind of looking across those two strategies, very simply, what's the relation between them? What do they estimate? Okay, and obviously under what kind of assumptions? And I basically want to just make two main points in my talk today. The first one is a broad kind of equivalence point, where what I'll be doing is I'll be giving explicit assumptions on the underlying structural economic environment, as well as on the regressors, which here in kind of equation one are like in particular the kind of notion of a macro shock, as well as the measure of the policy regime, such that both kind of our conventional idea of regressing on policy shocks, as well as here this kind of interacted local projection, deliver a kind of unique, well-defined notion of policy causal effect. So they share the same broad kind of estimate. At the same time, and that will be kind of an important secondary point, is that this notion of policy causal effects is inherently a high-dimensional object. So for example, for monetary policy, you can think of I change interest rates today and for a couple of quarters, or I announce today that interest rates will be elevated for a couple of quarters in the future. So it's a high-dimensional space of possible treatments, possible policy treatments, and so causal effects you could learn about. And that in any given application where you have a measure of a policy shock, or you run something like equation one here, you are generically going to be recovering different slices of that common high-dimensional space of policy causal effects. And in particular, in some applications I'll be kind of going through that built very heavily off of very nice previous work, what we'll be seeing is kind of one thing kind of known, that in the monetary policy case, our typical regressions on shocks tend to isolate what I would call a more transitory treatment, so interest rates being revised for a couple of quarters, versus these kinds of kind of systematic policy regime interacted regressions tend to give us something that looks more like a persistent interest rate treatment. So in a kind of very indirect way, it teaches you about something that you would kind of, if you just look at it, would call forward guidance, okay? Even though it's kind of a very different strategy of getting at something like that. So that's the promise, the roadmap for today. So I'll kind of try to, in particular now, elaborate on the kinds of DGPs and assumptions on regressors such that all of that logic actually hangs together. And we've decided to do for this talk is to actually kind of give things like the simplest way of communicating the core intuition in a pretty simple two-period model. Once you get that, you'll kind of get a lot of the core ideas of what I talked about on slide one. So here's kind of my structural two-period environment that I'll use to communicate the main ideas. So as usual for these kinds of exercises, what's the environment you look at? You choose the three equation New Keynesian model. Okay, so that's going to be consisting, well, three equations, two non-policy and one policy, one monetary policy rule. The two private sector blocks are just as usual, the IS curve as well as an NKPC. Very standard. There's nothing particularly exciting going on here. I just want to kind of flag 2 points. First point is that this is the simplest version of that model where I have kind of no kind of backward-looking internal propagation. So this is a purely kind of forward-looking model, no kind of endogenous states. Number two, on the shocks, for reasons that'll become clear, those two shocks are going to be both MA1s. Okay, that'll just allow me to make a somewhat interesting point. Okay, so a demand shock, a supply shock, both MA1. Good. Now let's switch to the second part, policy. And there we usually would close the model with, say, simplistic Taylor type rule, feedback, say, from inflation to interest rates. And then we have, say, here from what I want to talk about, two notions of shocks to that. One is kind of our textbook idea of a contemporaneous monetary policy shock. announced at date T, it's a deviation from the rule at date T. And then there's a one period I had news or forward guidance shock. Announced at T-1, it's a deviation from the rule at date T. Okay. Now, with how I've set up this environment, with no kind of endogenous propagation, nothing backward looking, and the shocks being kind of at most MA1s, this economy here will basically stop after 2 periods. Okay, so I can stack all of the impulse responses to my 4 shocks, to my demand, supply, and my 2 types of monetary shocks into 6x1 vectors, impulse responses. Theta D giving me the IRFs for the demand shock, theta S for the supply shock, and then theta V for my 2 monetary shocks. Okay, now what I want to do as an econometrician is I want to learn about policy transmission, policy causal effects. And usually what we then call our object of interest is the blue guy, okay, theta V. That's what we typically want to learn about. I will very briefly review. There will be nothing particularly exciting on what regressions on policy shocks deliver us. And then I will turn to a strategy that leverages variation over time in systematic conduct of policy. So variation over time in the Taylor rule, say the Taylor rule coefficient. Okay. So let me begin with a quick recap of simple regressions on policy shocks, where the top of the slide will be exactly like you've all seen this a million times. The bottom of the slide will have a maybe somewhat subtle, not super obvious point that's still going to be important. Okay, so what do we usually do? We think we observe some kind of variable WT that is either ideally directly some monetary shock of interest, some shock of interest. So here V0T or V1T, then it's a forward guidance shock or a contemporaneous shock. Maybe it's just an IV for those, so it's noised up. Maybe it actually loads on both of these. So both of these omegas could possibly, those weights could possibly be non-zero. Now what you do is you take that object, and at least here in population, I'm making my life easy, no distinction between VARs, LPs. I just regress on that W. I regress some outcome of interest Y, which may be output, inflation, the interest rate on that IV, and I report my coefficients. What will those be? Well, those will be just a weighted average of the blue theta V guy that I've defined before, right? The weighted average of these policy shock causal effects. Now, here's the first minor twist that I want to talk about, which is what we usually do is we think about policy transmission and policy causal effects as the effects of shocks relative to a given rule. What you can also do, and what I would actually maintain is both like a little bit easier to interpret and how we usually communicate our results in the papers we write, is not in shock space, but in instrument space. So concretely, what I mean by that is look at the model, look at just the IS and NKPC in isolation, and solve those for output and inflation given any interest rate today and any interest rate tomorrow. That gives you now the causal effects not of shocks, which are propagated through the Taylor rule, but directly of the interest rate themselves. Okay? Kind of here mathematically, the way this looks like is how do you move from shock space to instrument space? You just look at the combination of shocks that moves interest rates by 1 unit today and not tomorrow, or not today and by 1 unit tomorrow. Okay, so you can freely in an invertible way shift between instrument space and shock space representations. Okay, and then what you can do is you basically just run this regression on the W. You do that for your instrument for the interest rate. That gives you an IRF. You store those coefficients. That's your treatment. That's here a 2x1 vector. And then you do the same for output and inflation. Those are the treatment effects, the causal effects of that. Okay. Just very quick aside before I progress. Why is this when is this exactly kosher to do? No harm assuming here the economy does stop after 2 periods, right? Which kind of what's going on under the hood is there's an equilibrium selection going on according to the Taylor principle that you actually don't have kind of future sunspots. That's why kind of structural work usually thinks of shock causal effects and not instrument causal effects, because rules play 2 roles on equilibrium instrument path, and equilibrium selection. I'm abstracting from the second one here. So that's just a quick aside for those coming from more of a macro theory angle. Good. So let's now get to the actual kind of approach that I want to talk about here, which is suppose we now instead observe data that come from 2 different policy regimes. So in my previous economy, from either you observe the same economy in 2 disjoint samples over time, or that same economy kind of with the same NKPC and IS curve exists, but there are 2 different monetary authorities and kind of cross sections of countries that follow different rules. One of them will follow what I will call a baseline rule, which is phi pi equal to some coefficient phi pi bar. And I will denote impulse responses under this specific rule with bars. And then there's another monetary authority that has changed over time or in the cross section of countries that is much more hawkish. that has a much higher coefficient, phi pi h. Okay, and I will denote IRFs under that different regime by h superscripts. Now, how can we use that? Well, here's a preliminary observation that goes back to my previous work with Alistair, which is that if you want to know how, say, the demand shock or the supply shock propagates in the H regime, when monetary policy is really hawkish, well, it's equal to how this same demand shock or same supply shock propagated under my baseline bar rule. So that's the first term, plus two well-chosen contemporaneous and future monetary policy shocks that turn the initial rule, the baseline rule, into the hawkish rule, so lead to interest rates being higher. Okay, so you can always decompose impulse responses in that specific way. Okay, and again, the intuition is just that here in this class of model, like in the three-equation NK model we wrote down, policy only matters via the path of the instrument, here the interest rate. And so via shocks to the baseline bar rule, we can enforce the counterfactual H rule and get IRFs of the demand and supply shocks under that rule. Okay, good. Well, once you have that, once you know that this is the shape that impulse responses take, let's now contemplate running the following interacted local projection. We take an outcome of interest, GDP, inflation, or the policy instrument, the interest rate, regress that on, say, either the demand or the supply shock. I'm going to denote this by generic epsilon JT here, as well as, and for now I'm making my life very easy, an indicator of the regime, and I'm assuming I'm observing two disjoint far apart subsamples. Again, for now I'm making my life really easy because this is just for intuition. So I'm going to have a dummy zeta t that tells me, am I in the baseline regime or am I in the hawkish regime? Okay, and now I run this interacted local projection here, and I'm going to be looking at the coefficients on the interaction, the delta y's. Now, what you're going to find is, and that's kind of immediate from the previous impulse response characterization one slide ago, is that running this interacted local projection, equation 2, is equivalent with outright regressing on a linear combination of monetary policy shocks, your shocks, the omegas, that map, kind of following a demand or a supply shock, the baseline rule into the counterfactual, more hawkish H rule. So specifically, what kind of, you run this regression, you run it for the instrument, the interest rate, you store those coefficients, call those delta I. Now you, in boldface because it's 2, now you run the same interacted LP for output or for inflation. That gives you two more coefficients, delta y and delta pi. And what's going to be the case is that those are just equal to whatever you estimated for the instrument, that's your treatment, pre-multiplied by the causal effects of that treatment. And now you see why I moved from shock space to instrument space, right? Because now it becomes very easy to kind of read off what you've estimated. You've estimated a treatment, you've estimated its associated, uniquely defined kind of policy instrument-induced causal effects. Okay, so that's kind of the two claims then from the introduction. Because kind of going back to the previous work I have with Alistair, changes in rules in this simple environment here can be enforced through changes in shocks. You can invert this logic and say an interacted LP like equation 2 is as if you're regressing on some mixture of policy shocks. However, and that's the treatment heterogeneity, generically for any demand or supply shock you put in there, you'll get a different treatment. Say the demand shock is like IID, the supply shock is an MA1, then in the supply shock case, you identify persistent treatment. In the demand shock case, it's just a one-off interest rates only move today treatment. Versus for a monetary shock, if it's a contemporaneous one, well, that just moves interest rates today. If it's a forward guidance one, it moves interest rates both today and tomorrow. So each one of those generically will identify a different slice of this here 2x2 matrix of policy causal effects of an outcome of interest. And those were kind of the two claims from the introduction, just now obviously in a very simplistic, highly restrictive environment. So the rest of the talk is all going to be about generalizing both the underlying environment and making clear what the assumptions on the regressors are going to be, which here was structural demand and supply shocks and like an indicator for the regime where the regimes were far apart. So this is not an empirically relevant setting. This is an intuition building setting. Okay, good. Yeah.
Just keep in what if here the only coefficient that changes is the response of the policies.
Yeah.
can you generalize that in this particular?
Right,
example?
right. Okay, so what was going on here? So let me, this is a perfect transition. Let me list all of the limitations of this environment we just talked about. Okay, so limitation number one that I think was important is, but that'll be easy to address, is this was a two-period New Keynesian model. We'll like now obviously need to go beyond that. The second one is, I was assuming that, and this is now still not addressing your question, I was assuming only policy is changing, but even more restrictive, it is only changing kind of one-off across two permanent long-lasting samples, right? I want to allow for policy to be stochastically changing over time and maybe even in ways that kind of endogenously respond to the economy. Inflation was high, so now we care more about inflation stabilization. I want to allow for that. And then the third one is what you're getting at, which is, what did I allow for? The only changes in this system here over time were in monetary policy design. What if either maybe a richer set of policy instruments is changing over time? Perhaps when we enter the ZLB, it's not just interest rate setting that changes, but we rely on other unconventional monetary or fiscal instruments. Or that the private sector structure itself could be changing over time. So for all of these extensions, I will now work towards. So that's what I regard as the meaningful limitations of what we've seen so far. Did I? No, that didn't get it. Oh, okay. Good. So here's like a one-slide sketch of where I want to go, and then I'll go into the actual detailed results. So what I want to arrive at is some kind of conditions on environment and regressor, such that the lessons of the simple example extend in the precise sense of there'll be kind of a checklist of conditions on regressor such that you run this interacted local projection, you run it for a policy instrument, store the coefficients, happy to call that a treatment, store the coefficients for outcome, you're happy to call that the treatment effects. What are the assumptions I need to make this kind of desired takeaway tick? Okay. So here's a preview of where we're going to be going. I'm going to be going beyond the two-period New Keynesian model by looking at a kind of general but linearized family of structural models. That's exactly as in my work with Alistair. Now we allow for stochastic and possibly endogenous switches in policy design over time. And then as a third step, allow for further kinds of state dependence, variation over time or in the cross-section of countries in shock propagation that doesn't come from policy, but comes from changes in the private sector structure of the economy. That's the claim of environments to which we're going to be able to speak. Those environments, as I generalize, will go hand in hand with conditions on the regressors that I'm going to be requiring. As a quick preview of where it's going to be going is this epsilon JT, this kind of shock event, needs to be some kind of fixed macroeconomic event that itself is not shaped by the systematic policy measure you're including. A primitive shock, like an oil price disturbance, will say always do the trick. For reasons that are kind of interesting and I get into, usually simple kind of reduced form walled innovations, at least when you do it in a time series application, will not do the trick. Okay, and there'll be interesting kind of economics for why that's the case. Second thing, on the systematic policy measure, it can in principle be highly endogenous. It can be that systematic policy design is changing over time, precisely say because there was high inflation in the past, so you care more about inflation now. But it should shape the propagation of your conditioning event, this zeta t variable, only because policy has changed. Right? And not that, say, past inflation was high. Now, not only you care more about policy, but also price setters adjust their prices much more frequently. Then you'd have an additional margin that you're capturing and you shouldn't be capturing. Okay? So the roadmap is going to be, I'll begin with a general linear infinite horizon model. I'll use that to illustrate the required conditions on the shock variable. And just 1 second, Diego. And then I'll add kind of on the environment, I'll add policy switches and further kinds of non-policy state dependence. And that'll allow me to discuss requirements on the systematic non-policy policy regime measure zeta t. Yeah, Diego.
On the second environment, exclusion restriction, isn't that oftentimes not plausibly satisfied in empirical settings? So it's very hard to argue the change in the propagation of the shock only works through the change in the rule.
Yeah, well, so it is clearly going to be like an application dependent question. Then when you're saying I'm looking here at, say, some primitive event like your oil price disturbance, for example, and I look across two different subsamples, or more generally stochastically covary this with, say, a measure in one of our applications that builds on previous work with a measure of the FOMC's composition. And you then want to see, does that also covary with more broadly the state of the economy? Because we think, say, any shock propagates differently in a boom and a recession. You'd want to rule out that. Yeah. So clearly that's what you're going to require. Otherwise, Well, I can tell you what otherwise you're going to get. There's kind of some characterizations in the paper of what your estimate is in that case. Say you have two time varying blocks in your model. So this is a quick preview. Suppose policy is time varying and say the slope of the Phillips curve is time varying. Then what you're going to be getting, what your deltas will correspond to, is a weighted average of two sets of shocks to the instrument and cost push shocks. That's what you're going to be recovering in that case. Okay. So let's get into the environment. And let me begin with the kind of two steps as I previewed them, beginning with permanent policy regimes just now. So same as in the simple example, but now in a much richer infinite horizon linearized class of models. So this is just a recap or restatement basically of the work I've done with, or the environment I studied with Alistair. So you have two model blocks, a private sector block and a policy block. A private sector block is equation 3 here. So in terms of notation, first of all, the x's here are private sector outcomes. So think of GDP inflation in the previous example. Boldface denotes sequences. So this is kind of a sequence-based characterization, implicit characterization of an equilibrium. What equation 3 is, it is a connection between current and expected future at each date values of these endogenous private sector outcomes as a function of two objects, as a function of the date t shocks, non-policy shocks hitting the economy, ET, as well as the date t revisions of the policy instrument, Z, which here for simplicity, I'm assuming for now is just a scalar variable. Okay, so equation 3 is doing something like stacking IS curves, NKPC curves, investment demand relations in bigger models, and so on. And as we kind of detailed in a lot of detail in the previous work with Alistair, a lot of kind of typical linearized DSGE type setting, including hang type environments, just map into a structure like this, where these matrices HX, HZ become hard to characterize, but they exist. We can write down the private sector block in that particular way. Then there's a second block, which is here for now the not stochastically varying, because it's my first extension, the policy rule, giving us the policy instrument Z here as a function, feedback function of the various endogenous private sector outcomes, the x's, as well as possible shocks to the policy instrument. So say the monetary policy shocks of the previous setup. Okay, so V's are policy shocks, E's are non-policy shocks. Equations 3 and 4, once you solve them, give us a mapping from these exogenous inputs, the shocks, into outcomes, which are the policy instrument, as well as endogenous private sector outcomes. Okay. Now, in this environment, just as in the simple case, I can now define, and this is again where my estimates are going to live, these matrices here, theta xz, that tell me for each path of the policy instrument, which is now an infinite dimensional sequence, what are the associated causal effects on output and inflation? Okay, so you have, say, an AR1-ish path of the interest rate that does something to output. You have an ARMA path that again does something to output. That's what this overall matrix is pinning down. And the scope I kind of already briefly sketched, and it's of this environment, it's discussed at length in our previous work. Great. So now I am still being very simplistic on the policy regime. I will for now still assume that you observe data from two distinct policy regimes, either over time or in a cross-section of, say, different entities, different countries, and you run the same kind of interacted local projection as before, just now in this much kind of richer class of infinite horizon DGPs. And yet again, you focus on the delta y's, those coefficients. And somewhat unsurprisingly, given kind of the intuition I've tried to communicate, you get exactly the same as before, where you now just 1 second, sorry, where you run the interacted LP here for the policy instrument on the left-hand side, that gives you a delta Z path, that's your treatment path. You redo the same for the outcome of interest, you get the associated treatment effects. Yeah. Yeah.
The exchange rate example is one where it's natural to think about causal effect as being, like in our paper, a combination of the effect of monetary policy and say like some direct, natural shock to the exchange rate. So that's exactly.
Fantastic. Yeah. So that actually connects in really nicely also with the point here at the bottom, which so in your example, and what I can more generally talk about here, suppose multiple distinct notions, say, of a policy instrument are changing, which in your case would be so for given the UIP, given UIP violations, you can kind of independently control interest rates domestically as well as the exchange rate, and you get like a combination of treatment effects for like the interest rate, real interest rate treatment, and the exchange rate treatment. Now, in your case, given the specific kind of right-hand side here, measure of a shock you're including, it ends up being the case that the interest rate doesn't move all that much, and you see a lot of movement in the exchange rate. So what you're then getting is this kind of causal effect of the specific path of the exchange rate. If, say, here in this setting that I talked about, suppose what you have is monetary policy conduct changing over time, but it's high dimensional, not just in the sense that you can move rates today and tomorrow, but there's also, say, QE going on. Then what you would do is, like, you have a two-dimensional instrument. You put that on the left-hand side twice, you get two treatment paths of what the QE path is and what the interest rate path is, and you get the causal effects of this associated joint treatment of two instruments. Same if also fiscal policy is changing, you would put some measure of transfers or government spending or something on the left-hand side. And that's then exactly also the extended reply to what I tried to say to Diego, that in some sense there's then nothing special about policy, right? It's just the assumption of what is it that is time varying, and here varying with the measure zeta. In this simple case here, just the 0-1 indicator. So before I now transition to the kind of final and richer environments, I just want to make kind of a visual illustration of the treatment heterogeneity point. I want to very quickly show a couple of simulations from a structural model, just because I think this really drives home the point of the kind of infinite dimensional space of possible treatments and their associated causal effects. So what I'm going to be doing is I will look at the famous kind of linearized Smets-Wouters DSGE model, solve it with their monetary rule, solve it with a different monetary rule that I've made up, and the details of which aren't really important for our purposes here, simulate from both kind of samples with the two different monetary rules, run the previous interacted local projection for all of the various shocks in the model, which are the same across the two regimes, and then plot those delta coefficients from the previous slide. So what you're seeing here, first of all, in the top right, what am I doing is for the red line here, I'm looking at their cost push inflationary disturbance. That's my shock, my epsilon JT. Now my zeta T, my policy measure, is my 0-1 looking across my two monetary policy rules. And the top right just collects the coefficients on interest rates. Okay? So that then, in kind of how I've talked about it, is your treatment path. That's something the econometrician could estimate without knowing the structure of the model. That's just what the LP would spit out. The same econometrician then runs the same interacted LP, but with output and inflation on the left-hand side. They would then get the treatment effects you see at the bottom. All of that you can estimate just without knowing the model. What you cannot get without knowing the model, what is useful for us to understand things, is the top left, where I'm kind of showing this as if monetary shock path that turns, given the inflation disturbance, the first Smets-Wouters rule into my second made-up monetary rule. And you see here, this kind of looks like a pretty normal monetary shock, right? Where it's a kind of a large contractionary shock at the top, and then you're pretty close to zero, but like still somewhat elevated. So it's like this somewhat gradual monetary policy disturbance, as if disturbance, whose causal effects you're getting. But now, and this is the main point of this slide, redo this for the different shocks of the model, right? And in each case, you're getting a different slice of the overall space of causal effects, which corresponds to a different as-if path of monetary policy shocks and associated then different treatment effects. Okay, so here's just a bunch of examples. What do I want to kind of take away? Well, you see a lot of different colors that don't overlap. So the point is just that by shock you're including, the treatment you're isolating is quite heterogeneous. And actually here it's also relatively persistent usually. These are persistent, sometimes changing in sign interest rate treatments, which is just a reflection of the fact that non-policy shocks are typically persistent. And you look across somewhat persistent policy regimes of how they propagate. So the as-if treatment you're isolating also ends up being relatively persistent and is not what we tend to get if we just regress on a contemporaneous policy shock. Okay? And those observations will come back to loom large in our empirical applications at the end. Okay. So that was generalizing the environment. I promised that generalization would allow us to, even with the simplistic just two regimes, would allow us to say something about the required properties of the epsilon JT variable, whether it needs to be kind of a primitive structural macroeconomic shock. Well, what it needs to be in general is it needs to be some kind of fixed event, an event that's kind of repeating over time whose propagation changes with the zeta t variable because of policy. You can easily ensure that, or in these applications here, by it being a primitive structural shock. That's kind of by construction a fixed primitive event. Any kind of more generally, even reduced form kind of date T news that is not itself shaped by policy would also work. Kind of as in your in the exchange rate application, just kind of an exchange rate surprise. That's like a mix of different underlying primitive shocks. That's entirely fine. What's not fine is if you do this over time, say across two different policy regimes, and you'd want to do it with reduced form innovations, simple world innovations, because those themselves are shaped by policy, by the time varying policy. So you're not kind of comparing apples to apples anymore. You're not comparing how the same apple, well, this is a bad analogy, propagates over time, depending on the policy regime. You're changing both the conditioning event and its propagation. So you're not learning purely about policy causal effects anymore. More generally, I don't have time to get into this, but this was at least somewhat of a surprise, at least to me going in, is previous work with Alistair, we've argued that just knowing reduced form second moments plus policy causal effects allows you to back out counterfactual reduced form second moments. That mapping turns out to not be invertible. You give me autocovariance functions pre and post policy regime change, even if only the policy regime changes and nothing else, this mapping does not have an inverse. You can learn something, you can't really learn enough. So it kind of connects in an interesting way, I think, with the Musa paper on exchange rate volatility. You can talk about that offline if you're interested. It just turned out to not work as well as we kind of initially thought going in. Yeah.
So I feel like on many occasions macroeconomists are trying to orthogonalize their shock series relative to relative to these events. Is sort of saying that in some cases that might not be such a good idea, or at least you can't draw a direct analogy to that orthogonalized shock series that what you get from that shock in the model, which is actually what people are often trying.
Exactly. Yeah, no, I agree. And if you're doing it via, so here the kind of reduced form VAR kind of past projections are kind of trying to do that. And the same as if you have a direct measure of a shock, but you orthogonalize with respect to further lags. If those are themselves kind of shaped and co-vary with this time varying policy regime, that's not going to work here. Yeah.
So I guess in that setting, it would be better to model the persistence, or you would be better off modeling the source of the dynamic.
Yeah. And then, yeah. Okay, great. So let me now progress to the richer settings that allow for kind of more kinds of particular stochastic time variation. So here's the first kind of meaningful extension then of the underlying DGP. I'm going to keep the private sector entirely unchanged, but now rather than explicitly writing down a policy rule that may be changing over time, there's a myriad different ways of doing that. I will take a shortcut here that actually is for our purposes exactly what we want. I will just say policy in equilibrium is some reduced form mapping from the histories of shocks. Now we're going to denote by epsilon. It's both the private sector shocks, DEs, as well as possible policy shocks, as well as, because I want to nest Markov switching DSGEs, so like kind of Bianchi, Melosi, and so on. I'm going to have an additional variable S. That's my state of policy, right? I could switch from active money to passive money, for example, or switch across differentially hawkish monetary policy regimes. So I'm just going to replace the policy block by this reduced form solved out equation. This is implicitly assuming equilibrium existence. That's what it's leveraging. But beyond that, why is this a nice way of writing down the equilibrium here? Is that, well, I don't need to exactly say what policy is. It could be exogenously switching over time, like in a lot of the Markov switching DSGE type settings. It could be endogenously switching over time. If past inflation was high, now the coefficient on inflation in your Taylor rule is going up. There could even be some nonlinearities in how you set policy. Okay? The key is, and that's what's making all of the future results take that, conditional on whatever this mapping into the policy instrument path is going to be, you still have that linear mapping from that path into private sector outcomes. That's what kind of all Markov switching DSGEs in our usual way of linearizing around a common deterministic steady state look like. It becomes hard on the computer to solve these models because you as the structural macroeconomic modeler need to solve for this mapping. For my purposes here as an econometrician that tries to just figure out what their estimand is looking like, I only need to know that this mapping exists. So that's what I'm going to be assuming. I do not need to characterize it, because conditional on having that, the mapping into private sector outcomes is very straightforward. Okay. So once you have that, I now get a somewhat more interesting kind of characterization of what the interacted LP estimates that has some conditions on the policy measure zeta t. So I will suppose zeta t is some date t measurable random variable that I will say is allowed to depend on the histories of shocks from date t minus 1 into the infinite past, on maybe, if I have that, my policy regime indicator st, this Markov switching variable, as well as all contemporaneous shocks except for the one that's in my LP, so mine, everything except for J. I run the same LP as before, I get the exact same interpretation. So what's going on here is epsilon jt here again is that kind of fixed event, that shock. Zeta t is now some random variable that is going to have two properties. Number one, co-varying the shock epsilon jt with zeta t moves the policy instrument in some way. Delta z is not zero. I mean, if it's zero, this statement is still going to be true, but it's going to be trivially true. But in general, the requirement is delta z is not zero. Then you have some kind of treatment you can learn about. But now if you look at the conditions on zeta, it can actually be highly endogenous. It can be the case that if past inflation was high, you now care more about inflation stabilization. But because of my assumptions on the environment that the only time varying thing was policy, I know that if I have this interacted term here not being zero, it has to capture the effects of the time variation in policy, because that's the only thing here that's changing, right? So I'm baking in a lot by assuming here the stability of the private sector block and that there is stochastic variation in policy. Once that's the case, that can be highly endogenous, as we're seeing here. It just cannot depend on contemporaneous epsilon jt, because then you would again co-move conditioning event and propagation. Okay? But of course, that now raises the very obvious follow-up question of what if the dynamic propagation of epsilon jt changes with zeta t for other non-policy reasons? And that's what we've already been touching upon in a lot of the back and forth we were having over the last couple of minutes. So here's then the kind of final extension of the environment before I then get to the application in the last 5 minutes, which is now I go back to the private sector block, and I will now allow the coefficients of the private sector block, so the h's here, to depend on a further random variable m. I'll talk about the interpretation of that in a second, but now that's just now going to be my new private sector block. And then I'm going to have the same reduced form solved out equilibrium mapping for the policy instrument. So first little observation is that now once I have this time variation indexed by this random variable m of the private sector block, policy causal effects themselves become time varying. They depend on m, right? If you have a high slope of the Phillips curve, interest rates propagate differently than when you have a shallow Phillips curve. So what kind of does a setting like this nest? Most obviously, if you kind of look in a cross-section of countries, say in the exchange rate application, these countries may have different fundamentals, right? They may not just differ in whether they're floaters or peggers. They may have differentially developed financial markets. They may have differential slopes of the Phillips curves, MPCs, and so on. The same logic would apply over time, where kind of the formal justification is you have a time-varying aggregate state of the economy and you linearize around that, okay? Say your initial expansion point is in a brisk boom where MPCs are low. Now and if over time the economy develops, you're in a recession. Now MPCs are high. The Phillips curve is more shallow, something like that. You would get time variation in this private sector block. Okay. So once that's the case, you're going to get two additional subtleties and complications on interpretation. So first of all, what I'm going to require now, and this kind of is considered like reflects the discussion we've been having over the last couple of minutes, is I now need this variable zeta t, same requirements as before, but now I also need it to be independent. I mean, that's like an easy sufficient condition for me, to be independent of this additional variable m, okay? In that case, it is going to be the case that as this shock epsilon jt differentially propagates, it propagates differentially with zeta t only because policy is changing. But even that is not quite enough to kind of get us home free in terms of easy interpretation. This formula hints at why that's the case. Let me elaborate a little bit. So this thing we kind of just talked about, zeta t must shape propagation of epsilon jt not via any other channels, only via policy. But even then, even if that's the case, it may be the case that when as m is varying over time, the effective policy treatment you're isolating through that interaction is also changing over time. right? And this will be kind of very familiar for those of you coming from a more applied micro tradition, where you have kind of changes in the treatments. You're isolating a weighted average of treatments over time, but because the treatments are changing and the treatment effects are changing, you're going to require some additional kind of monotonicity conditions so that you don't get sign flips, right? You don't have negative weights, so you don't get like you cause something a negative causal effect, even though every individual causal effect is positive. And that's kind of talked about in the paper at quite a bit of length, where we characterize what those weights here are and give an easy sufficient condition and talk about of when those are going to be uniformly positive. But you do need to address that, right? Otherwise you run into additional issues. Okay, so now in my last few minutes, I want to briefly address the kind of more applied question of what in kind of some existing prior work, I'll just briefly recap, what do you actually estimate under kind of the, and how does that relate to the kind of the existing policy shocks we have? So here's the point I want to make. So first of all, on monetary policy, in monetary policy applications, our textbook notions of shocks tend to isolate rather short-lived interest rate treatments. So in my notation here, that's you learn something about the first or the second column of this data xi matrix, or like weighted averages of the first couple of columns, okay? Which is not great for the policy counterfactual work I've done with Alistair, because there what we want is this entire map, right? We want to, for counterfactual evaluation, we want to know the effects of very different interest rate treatments at different horizons. Now, there is then a literature that kind of motivated us to write this paper that leverages time variation in the conduct of systematic monetary policy. And the one paper I want to reference in particular in my application here is this work by Istrefi, Hack, and Meyer on kind of leveraging variation over time in the composition of the FOMC and asking, interacted with that, how do fiscal shocks, or in an application we do, how do oil shocks propagate over time, okay? And of course, we have now kind of worked quite a bit of what our preferred interpretation of the estimand of something like this is. You run it for the instrument, you run it for outcomes. What we haven't addressed yet is, well, what specific slice of this high dimensional space of treatment effects gets isolated? Yeah. Yeah.
Mostly about short-lived rate treatments.
Mhm.
Is that not partly because people have, orthogonalized versus, previous?
Yeah, but
So they, there's some, the earlier version of the shock, which
Mhm.
have that.
Yeah, but then I guess it like kind of in those papers, it then feeds into your identifying assumptions that you're saying, I want to have that orthogonalization, otherwise I'm not willing to call it a shock. But if you weren't,
Yeah.
right, then
I mean, it's possible that you could go back and reanalyze some of those shocks that you're considering, and
I agree.
there's some other information, like for example, Romer and Romer.
Mhm.
Like poker was kind of a persistent thing. But
Yeah.
it's a question of how you use that information.
Great. Yeah, no, entirely with you. Even like on as a very quick aside before I then get to the results, something like the Bauer-Swanson kind of more persistent that are supposed to speak to more persistent interest rate treatments, like the forward guidance stuff, given the controls that are included, even those tend to give you something more like much less gradual than you would have expected given the labeling. But I'm entirely with you that may be an artifact of the specific data treatment. So here's then just briefly some of the results. So this is just a quick recap of, given the orthogonalization of what's going on in Roma and Romer, that's kind of in our replication of their analysis, that's the interest rate treatment you get. That was kind of my claims about it being more transitory. And those are then kind of the kind of output inflation responses they would be reporting in their analysis. Now here is our version of, say, the Hackis-Treffy-Meyer. There's various different applications in the paper itself. Here interacted with a measure of an oil disturbance. It's kind of a mix of oil demand and supply. And the key point really here is the left one. And that's, you see the same in kind of the fiscal shock in their paper. You see the same in some other papers we're discussing in our paper, that it's a much more gradual interest rate treatment just because the shock itself is persistent and systematic policy conduct is persistent. And then you get kind of associated here more gradual causal effects that don't look as big as what you would have expected, say, in models with a forward guidance puzzle, where these delayed interest rate changes give very meaningful boosts. This is kind of in magnitudes very comparable to the Romer numbers. And I'm out of time, so let me here just wrap up with those thoughts. So kind of thought about what these kind of interacted LPs with time variation and systematic policy conduct, what they estimate. It's kind of, there's an equivalence point, there's a treatment heterogeneity point. Those are the two kind of main points I was hoping you guys would take away from this. And then a fair amount of discussion of what do you actually require on the regressors for this to work out. As we've discussed, the requirements are high, just as they're high for us being willing to call something a shock. once that's the case, if you can convince your audience of that, it actually has the potential of kind of in a nice way complementing how we usually think about policy causal effect estimation. Okay, thank you very much.
Okay, we have a coffee break and reconvene at 10:30. After this session, the lunch for this group is in ballroom B upstairs. Go ahead.
Great. Thank you so much for including our paper on the program. It's an honor to be here. I'm Carrie Siani from MIT. This is joint work with Jinyuan Zhang, who is here from UCLA. The decision window, how budget timing shapes fiscal policy. In our paper, we study how economic news becomes fiscal policy. Specifically, we're interested in how state governments in the US incorporate information into their revenue forecasts and thus into their spending budgets and their actual spending. And we're interested in what the real implications are of the information incorporation for these state governments. Why does this matter? So state and local governments in the US make up about 15% of US GDP, and they're significantly institutionally constrained. Importantly, they generally have balanced budget constraints, so the revenue forecasts and their expectations for their future revenues matter a lot for what they actually are able to spend. The key institutional friction we're going to focus on is that while economic news arises continuously that can impact revenue forecasts, these spending budgets are generally made discretely at discrete points in time in a state's budget calendar. And these spending budgets are actual commitments. So in our data, we'll show that spending budgets explain about 79% of the year-on-year changes in actual growth in expenditures within state. I'm going to first summarize our paper in 3 pictures before getting into more details. The first picture shows the decision window that we document. So this is revenue forecasts at the state year level with a distributed lag against monthly news that arises at various months relative to the state's enactment of its budget. Each point on this coefficient plot represents how much that month's news affects the revenue forecast. So as you can see, there's positive coefficients in the 4 to 8 months relative to before the enactment of each state's budget. And we think of that as incorporation of information into the revenue forecast. And we call that the decision window. Importantly, the news that arrives before and after this window, this sort of off-window news, is not incorporated into the revenue forecast in the same way. That is, the coefficients are not significantly different from 0. And instead, we will show later that this news is informative because it's actually going to reappear as forecast errors and in future budgets down the line. So that's the first picture. We find this decision window for revenue forecasts. We'll show later that it also affects state spending. And second, it's going to have real effects. Here, I'm going to plot the decision window news effect on private sector employment within a state in blue, and in contrast, how news that arrives off decision window affects private sector employment in gray. So you can see there is a large and persistent effect on private sector employment for news that arrives within the decision window. That is not the case for off-window news. And this persists out to about 2 to 3 years. The third picture is about monetary policy transmission. So we show that in aggregate, if you look at state and local spending across the US, we observe that calendar quarter 4, so October through December, overlaps with a lot of the decision windows across US states. And so monetary policy surprises that occur in calendar quarter 4, plotted in blue, have a much more significant and persistent effect on aggregate state and local spending relative to similar monetary policy surprises that happen Q1, 2, and 3. We think of this as another potential institutional source for Milton Friedman's long and variable lags to at least for the state government spending response to monetary policy. So let me go into more details. So this is an empirical paper primarily. So what we're going to do is we hand collect data on state budgets. We're going to do it for 47 subnational authorities, including Washington, D.C., that have annual updates for about 30 years from 95 through 2024. And our empirical strategy is going to exploit cross-state variation in the initial governor's proposal date of the budget. And so that cross-state variation, which is determined basically by constitutions and statutory guidelines, is going to have a given national shock that might be common across states, is going to be in window for some states, i.e. before the proposal date, and for other states it's going to be outside of the window. So our first finding is documenting that there is this decision window. That is, there is a few-month period in which news is incorporated more so into the state's revenue forecasts, its budgeted spending, as well as its actual spending. We also document that the decision window has real effects. It has real implications. First, it's going to affect private sector employment within that state. So state-level private employment is going to have a 4 times larger response to news that arrives within that state's decision window relative to similar news that arrives outside the decision window. This difference allows us to estimate sort of a back-of-the-envelope dollars per job. We get about $36,000 of general state spending per private sector job year. Finally, we find decision windows gate monetary policy transmission to state and local spending. So we find at the state level the monetary policy shocks mainly affect state spending via the decision windows. And we think of this as a new institutional source for long and variable lags of the real transmission of monetary policy. Okay, great. So our paper contributes to 3 broad strands of the literature. So the first, there's a vast literature on fiscal spending and its real effects. There's sort of these subliteratures that also think about, I shouldn't call them subliteratures. There are other literatures that interact the real effects of fiscal spending with institutions, both at the state level, and then also think about how they interact with industry and firm outcomes. So a lot of the literature thinks about identifying the real effects of government spending using basically the orthogonal component of the government spending. So if there is some fiscal rule based on fundamentals X, then a lot of the identification of real effects of fiscal policy is off of the epsilon. So whether we think about variation in federal military spending or ARRA payments, that informs a lot of the way we quantify these real effects. What's nice about our setting is we can think about institutionally driven decision windows creating variation in the fiscal rule itself, which allows us to identify the real effects of variation in the fiscal rule. We then can show the full chain from the state's revenue forecast through to the enacted budget, to spending, and then to the real economy via private sector jobs. On expectations and information, we propose a simple forecast incorporation test that allows us to identify when the decision window occurs in the institutional calendar of these state governments that we think could have broad uses across other institutions that might face similar frictions. Finally, on monetary policy transmission, we document a new institutional source of long and variable lags arising from these sticky budget calendars. Yeah, Valerie?
It's a nice follow-up on Olive and Railroad.
Yes.
The labor contracts, the seasonality of them to.
Yes, that's right. Yes, exactly. So Olive and Tenrero 2007 document that the Q1 and Q2 monetary policy surprises matter more for output. And the argument there is about wage rigidities. You set wage contracts at the end of the year, they're set up in Q1. So that's how the transmission happens there. And we're showing exactly like the institutional side on the state governments. So let me talk through institutions and data, starting with an example from Massachusetts, since we're all here. Massachusetts fiscal year 2026 just ended in June 2026. The discussion of what happens during this fiscal year 2026 actually began towards the end of 2024, when the budget, the legislative officers, along with executives from the governor's office, meet with consultants, economists, actually from the Boston Fed as well, to discuss what is the consensus revenue forecast for the fiscal year 2026. That revenue forecast they develop is going to inform the governor's initial proposal, which is published at the statutorily determined date in January, before the fiscal year begins. So this proposal is going to be followed by deliberation by the legislative the House and the Senate of the state, that then culminates in the enactment of the budget that typically happens shortly before the fiscal year begins. And essentially what we're going to do is in the data, we're going to hand collect what are called the annual comprehensive financial reports. We get them for 47 states, that includes DC, so 46 states plus DC, for 30 years. And we're going to get the calendars of these dates of proposal, enactment, and fiscal years from NASBO. And the data is actually going to give us these enacted budgets and actual spending and revenues at the line item level on both the revenues and the spending side. So to be clear, what we're going to observe and what we're analyzing today is the enacted budget, I'm going to call the enacted budget, which occurs typically here. And we can compare it to what the actuals were realized in terms of both revenues and spending for the fiscal year, for a given fiscal year. Great.
Sorry,
Yes.
a great question.
Yeah.
So the way it works in the corporate sector, if there's bad news or material news, then companies have to file an 8K, right?
Yes.
By law. So I mean, so here you're not saying that there's no no effect of a shock that occurs after the
Perfect.
deliberation, but you're just saying that then will occur the following fiscal year, right?
Yes.
So,
So,
yeah, so that's like 2 days after they've started, executing their, but it's that's really bad news, right?
Good.
Closure of the Strait of Hormuz, whatever. You're just saying, well, that will then affect the following one, so that's where you get this variable lag, right? You're not saying it's a zero effect.
exactly. So there's a delay. I should caveat this with there are outside examples of really extreme shocks, like the 2008 financial crisis, like COVID, in which there were more revisions during the year. And we do observe the final budget, including all amendments. Our identification is going to exactly use what you're saying, which is like there's a proposal date. After that, the information is going to be incorporated less. But we can actually put some numbers on this, because now that we have this data on the enactment and the actuals for each year, we can just do a simple like variance decomposition. And we can look at, for both revenues and expenditures, the change in log actual year-on-year revenues and expenditures. We can decompose the variance into the budget and the execution components. And so we see for revenues, about 51% of year-on-year changes in actual state revenues within state is going to be explained by the change in the forecasts associated with the enacted budget. So the rest is going to be execution. Whereas on the expenditure side, about 79% of actual year-on-year changes in expenditures are going to be explained by the enacted budget. So the budget, it's the changes in the budget itself. So that goes a little bit to what you're saying, where there's only, there's 79% of the variation in actual spending comes from the budget. That doesn't mean there aren't changes outside of it. So this includes the whole sample, right? Clearly, the enacted budget matters for what actually gets spent. And we know from the fact state governments have balanced budget rules and restrictions that the forecast of revenues that they make will tightly tie into what they can actually plan to spend. So we're going to next look at how these revenue forecasts are incorporating information and thus how it affects the spending decisions and actuals. Okay. So we're going to do that by proposing a simple forecast incorporation test that allows us to identify what we're going to call the decision window. So to be clear, we're going to allow the data to tell us what the decision window is. And we're going to think, suppose we have some news, Z, some shock that could affect revenues. We observe it in month M, in state S, and for future fiscal year T. The question is, how is this information incorporated into the forecast revenue at the budget as well as actual revenues? So we can run 3 simple regressions that have on the right-hand side a common distributed lag of these monthly shocks with potentially different loadings. And on the left-hand side, we first look at the time of the budget revenue forecast, and these coefficients will then tell us how informative each of these month's shocks is to the forecast, so how much government officials are actually incorporating that news into their forecast. The second regression is replacing the left-hand side with actual revenues, which tells us the actual informativeness of this news for tax revenues. And then finally, we can compute a forecast, the equivalent of a forecast error. So there's some similarity if you think like to the Koibian-Gornichenko 2012 analysis, although what we're doing here is thinking about governments predicting their own revenues rather than an aggregate across professional forecasters. So the forecast error coefficients, sort of by definition, should be equal to the actual minus the budget coefficients. This yields a very intuitive set of tests. So you can imagine for the benchmark full information, a perfectly rational, forward-looking government official would then take the coefficient in the forecast incorporation budget regression, the first equation, should in every month be the same as how much that information actually matters. And then no news should actually predict forecast errors. Our decision window hypothesis, which is motivated by this institutional idea that these state government officials, both legislative and executives, have a discrete point in time when they meet and create these forecasts and spending plans. If there's a decision window based on that, then in this decision window, agents act as if it's full information, and so this should not, the news within the decision window should not predict forecast errors. But then outside of that window, they no longer incorporate new information, and that, if it is informative, will then predict forecast errors. There's a problem if we especially want to think about how the decision window affects real outcomes, which is there's no such thing as a perfectly exogenous shock, right? So any Z we try to identify is going to be directly correlated with the state economy's output and activity. And so what we're going to do is exploit cross-state variation in proposal dates that are typically constitutionally determined and statutory norms. Okay. Let me give an example with one shock across two states. So here, Virginia versus New Jersey, they both have fiscal years that begin July 1st, but they have different budget calendars. Specifically, Virginia proposes its initial budget in December, whereas New Jersey proposes it in February for the same future fiscal year in 2017. That means a given shock, so for example, the January 2016 big market turmoil that had an oil price crash that led to the S&P dropping by 5% on the month. This is a big negative shock that occurred after the proposal date of Virginia, before the proposal date of New Jersey. What we can see in the data is that Virginia had a budget for the following fiscal year 2017 that reflected an increase in expected revenues and a corresponding increase in planned spending of about 6%. Whereas for New Jersey, they actually cut their fiscal year 2017 revenue forecast by about 9% and accordingly cut planned spending by even more than 9%. Yes.
Outside the decision window, but let that all to be asymmetric. After the decision window, of course, I've decided, but before, that must be inside, although outside the decision window,
Good.
that must be my information set that I might have acted on.
Yes, that's right. If I am going to fully incorporate information at any point that I update, then all shocks before should be incorporated. And so there shouldn't be any pre-window forecast error predictability. We can test this directly, and we basically, excuse me, are able to reject full information updating. And I'll show you that in a moment. Yeah, great. So the way we interpret this, of course, this is just a one example, is that Virginia had its proposal date, it made its forecast of revenues and proposed an initial budget. And after that, it doesn't seem to have responded in the same way that New Jersey did to this big negative shock. We are going to generalize this example across many states to an identification strategy that exploits the staggered proposal dates across all the US states in our sample. And so the idea is we have different proposal dates. There are shocks that happen on either side of proposal dates for different states. When we add fiscal year by calendar month fixed effect, that absorbs the common shock, the common national shock component. So the identification only comes from the different proposal timing of all the states. The identifying assumption is that the proposal date is orthogonal to fundamentals, and we run some tests in the paper to make sure that that is reasonable. Okay. The map shows the variation in the proposal dates across the US. The proposal dates typically range from November through March with no obvious clustering geographically or economically. Okay. So we have some identification. Now we ideally would want a state month panel of shocks to revenue expectations. Absent something like this, we're going to construct a shift share measure that would move the revenue expectations and actual revenues. So what we do is we take the five of the main revenue sources across states: income tax, sales, charges, corporate tax, and severance tax. And we map each of these revenue sources to a national innovation at the monthly level. That's going to be seasonally adjusted. And we take that shock, that's sort of our news. We do AR4 residual of the monthly log changes, and we aggregate it back up to the state level using the predetermined revenue share. So this is like the shift and the share. And we then weight it further by this elasticity of revenue relevance on a national level. So this is the state specific. So it's going to be a state month panel of shocks to revenues. Equipped with this news shock, we can then try to identify where is the decision window. To do this, we're going to regress forecast changes on these monthly news where we are thinking about it relative to each state's proposal date. So note the difference from the first picture I showed you, which was anchored around the enactment date. For that picture, I showed that the decision window appeared many months before the enactment date. The nice thing in the data is we can observe the proposal date, so we can anchor directly on that because that's when the first revenue expectation and budget is put forth by the governor. And so by anchoring around the proposal date, we can see very clearly, sort of visually, the decision window. So we identify the sort of 1 to 5 month period prior to the proposal date at the state level as the decision window. So we've identified the decision window so we can implement directly this forecast incorporation test to see how information is, yes?
Just following up on Rafet's question, I get empirically that things from more than 5 months earlier don't empirically matter, but why?
Yes, so it doesn't directly map into a clear model. I think there's many behavioral stories. You have noisy memory, limited memory, fading memory, and you have recency bias. So there's those things that would suggest that really old news, even if it's informative, is not perfectly incorporated into your information set. So that's one, if you can imagine, that aggregates to government officials. But I know it's not a very satisfying answer, but I don't have like one clear model that explains that. Sort of what we describe as more of a discontinuity, because a lot of the sort of recency bias predictions would be something more monotonic than sort of a step change. Yes. Great, yes, and it does. And we will show that the off-window news does show up. Actually, that's the next slide, I think. Yes, it's one of the, I can show you this. So basically what happens is off-window news doesn't show up in this fiscal year. It shows up in forecast errors and then in future years' forecasts. Exactly, it doesn't just disappear, right? So here we can use these, this definition. Yeah.
The before the window not mattering today.
Yeah. So I think it doesn't matter for the expectations of the government officials versus doesn't matter for actual tax revenues. And so essentially what we're saying here is it's not being incorporated into the expectations of government officials, but that doesn't mean, maybe some of it doesn't matter, but at least some of it does matter because we do see some of it show up later on in actual revenues. Again, maybe it's clearer here if we look at the forecast errors. So here we can sort of implement our forecast incorporation test that I showed you using this definition of the decision window. So now we run a similar regression as I just showed you, except now I partition the news by time on the budget calendar into the decision window and before and after the decision window for each row. The first column shows how forecasted revenues respond to news that arises in each window with a strong loading and positive loading on decision window news. And the second column is the forecast error, which is the exact mirror. It essentially shows the decision window news does not predict forecast errors, but pre and post decision window news does predict forecast errors, which suggests that that news was relevant for actual revenues. It did help predict somewhat sales tax revenues, income tax revenues, but it wasn't incorporated into their forecast. So off-window news is informative, predicts forecast errors, but it shows up in later budgets as well. Okay, so we think of it as like just delayed, not necessarily forgotten. Great. So now we look at spending. Does this revenue forecast actually translate into different planned spending in the budget? So what we can do is use this slide I just showed you as essentially a first stage mechanism test to see how changes in the spending plan, the budget spending, loads onto sort of predicted changes in the revenue forecast, responding to shocks happening before the decision window, during the decision window, and after. Essentially, you can't really use the first stage in the pre or post decision window because it doesn't significantly predict changes in revenue expectations. So we just use the decision window news to instrument these forecast revenue changes. And we show that a 1% news-induced forecast revenue increase will increase the expenditure budget by about 0.4%. Okay. So these are not just plans on paper. We can show that this actually manifests in spending itself by replacing the outcome variable with changes in actual spending relative to the prior budget. And we find similarly that there is a response. A 1% news-induced forecast revenue increase will lead to about a 0.5% increase in realized spending. So I've shown you this whole sort of channel of shock onto news affecting the revenue forecast, affecting planned spending, and then realized spending. The question is, are there real effects? Do we care? So the first thing we can do is we sort of extend the chain to look at private sector employment at the state level. So here I'm going to narrow in further to the state industry level using quarterly data from the QCEW, private employment and wages for the two-digit NAICS over the same time horizon. So the idea is the following. In a given state year, you have a shock that happens within that state's decision window. It affects their spending. So if you are a firm in that state that sells a lot to the state government, that's going to be a shock to your sales. One way to proxy for that, we're going to use the BEA's share of industry output purchased by state and local government at the industry level. So that's going to be just constant across time for a given industry. So then that allows us to do essentially a triple difference where we look at the shock times whether it's inside or outside the decision window, and then whether the industry has a high or low share of sales to the government, the state and local government. So we include a whole suite of fixed effects, including any industry level shocks, any state specific shocks, or any state industry interactions, and then the same month fiscal year fixed effects we had before, so that the identification is within the same state year. Do industries that are selling more to the government respond differentially to news that happens within the decision window relative to outside the decision window? So here are the results in a plot. In blue, we plot the differential employment effect of news happening in the decision window on industries that are more government exposed versus industries that are less government exposed. So that's in blue, the decision window effect. In gray is the same thing, but for news that arrives off window. So two things to note here. One is that decision window news has a large and persistent differential employment effect on private industries that are more exposed to the government, whereas the off-window news seems to have a small and sort of transient effect. What's interesting is if you think back to our earlier discussion about whether off-window news matters, and I said that off-window news actually shows up in forecast errors and in later budgets, which suggests from the government perspective, these shocks eventually kind of sort themselves out. But on the firm side, you would expect to see that this off-window news eventually converges, but instead, because this is all cumulative, instead what we find is that there's a persistent differential for those government-exposed firms to decision window news. And this persists for up to 3 years after the fiscal year begins. So how do we think about this? So our interpretation is about timing. If there's a shock that happens within the decision window, that's going to affect same year spending. So firms that are selling a lot to the government have a lot less time to respond. If you imagine them as these more credit constrained firms, this has been shown in Bertrand 2020, that they might be credit constrained. Then if they have a reduction in sales from the government, they might not have time to adjust by borrowing from credit markets. And so instead they might have to cut employment, and that creates a persistent negative effect. On the other hand, if the same news happens off window, it gets delayed to the next fiscal year because firms can anticipate, we know from Valerie's work, they can anticipate what's happening, that they can incorporate that information and they have time to respond. They're going to have they're going to have a muted employment response to any of these news. So this story has a natural test. We can directly look at the difference between positive and negative news. So what we do here is we take decision window news and we separate it by sign. And we show that, consistent with this story of adjustment frictions at the firm level, that there is the persistent employment differential effect for government-exposed industries to decision window news is concentrated in the negative news, with less of an effect on positive news. So that supports the story of adjustment frictions at the firm level. Interestingly, when we do a similar analysis for state spending, there isn't as detectable of an asymmetry for state spending responses to positive versus negative news. So state governments respond similarly. And so that suggests that it's not the government creating the asymmetry, it's more a firm level friction. Yeah, Emmy?
I guess maybe you shouldn't say, is there evidence that the response of the spending itself was more or less the same to the within window versus not within window, just in magnitude, not, I guess.
Good. Yes, for the spending itself, we do have the reduced form version in the paper, but we should I don't think I have it here.
Christians, I don't know.
Yes.
Setting, it's very persistent. But I guess you would think of the policy variables being the government spending itself. So
right.
I guess comparing those to the government spending, then I guess whatever.
We will do that. That's a great point. Yes, Valerie. Yeah. Yeah.
California loves to deal with its budget deficits by just raising taxes and state.
Good. Yes. Yes.
And any indication of how much is going on with that?
Great. Yeah. So tax policy changes could sort of muddy the results a little bit. We do have a table in the appendix. We look at tax policy changes across all our state years, and they don't seem to load significantly on our decision window news. So it can't be the primary driver, but of course it could be, it could be a consideration. Good. Perfect. Yes, that's helpful. We'll do that. Yes.
I have a question about, have you thought about proximity to federal government budgets? In the sense that the extent that this is possibly driven by the 2008 financial crisis, the pandemic.
Yes.
Federal government spending on budget support could be particularly impacting your spending.
Perfect. Yes, absolutely. If there's a big shock like the 2008 crisis, the federal government will basically lean against our results. And we do find that's the case. If we take out 2010, fiscal year 2010, which the planning happened during the 2008 crisis, our results are all kind of stronger. We have a leave one out table in the figure where we take out every single year and we run everything, and it still holds regardless if you take out 2021 or 2010. But yes, that's a very good point. In general, if for a really large shock, the federal government will work against our results. Good. Great. So we think about this as firms not really being able to respond to quick shocks in terms of state spending on decision window. Okay, great. We can aggregate to the state level to understand how state level employment growth loads differentially on news arriving in the decision window versus outside. And what we find here is news that arrives during the decision window affects employment growth at the state level about 4 times more than similar news that occurs outside the decision window. And that premium still is similar in magnitude for wages. So This difference in similar news arriving either on decision or off decision window for aggregate private sector employment allows us to estimate kind of a multiplier effect where we think about a given change in state spending, how does that affect employment? And so just comparing the estimates that we have in the paper, we can estimate this sort of 1% decision window news driven revenue expectations driven change in spending at the state level will affect employment by about 1/3%. Okay. The identifying assumption there is that if you have some news, if it happens on or off window, that shouldn't have any differential effect on the private sector. So private sectors should generally should respond similarly absent the fiscal channel. So we can map this to about $36,000 of induced state spending per private sector job year, which is well in the range of the existing literature, though what we measure is slightly different because first we're using state spending, it's state general spending, and it's only private sector jobs. But importantly, a lot of the literature focuses on estimating off of these shocks that are essentially orthogonal to the actual policy rule. And what we're trying to do is estimate something off of the rule itself, given that the rule is driven from revenue expectations. And we can identify it off of the differences in the decision window. Okay. Finally, monetary policy. We're going to show that decision windows matter for monetary policy transmission. We're going to use the same on-off decision window identification, same outcome variables, same controls and fixed effects, but we're going to replace our revenue news shock, the shift share thing we constructed, with just standard monetary policy surprises. The outcome here is in blue, the budgeted spending growth, and in red, the actual spending growth responds strongly to decision window news, that is news that happens within the decision window for a given state. And so a contractionary monetary policy surprise occurring during the decision window has a strong effect on both budgeted and actual spending across a few different shocks in the literature. Okay. This effect also aggregates. So like I showed in the beginning, many of the state decision windows actually overlap with calendar Q4, so October through December. And so we can separate out the monetary policy surprises. Here I'm using the Bauer-Sanson 2023 monetary policy surprises, interact it with Q4 versus Q1, 2, 3. And on the left-hand side, we use aggregate state and local spending. And we can show in blue that monetary policy surprises that happen during Q4 have a stronger and more persistent effect on aggregate state and local spending as a share of GDP. We can map this to magnitudes by running the same regression except replacing the outcome variable with GDP changes. And that gives us a magnitude of about 10 to 20% of the total GDP response to the same shock. Right. So we think of this as a new potential source driven by budget calendars of these long and variable lags that Milton Friedman talked about. Great. Okay, so takeaways from the paper. The main thing is that budget timing determines what news affects fiscal policy. We show that by documenting a decision window, which then determines for each state which news becomes fiscal policy through planned spending and actual spending. And these decision windows matter because they gate the real transmission of shocks to state spending and to the real economy. We show a 4 times higher private sector employment response for in-window news relative to out-window news. And this is mostly driven by bad news. And we finally show evidence that budget calendars contribute to these long and variable lags of the real effects of monetary policy. A lot of institutions face similar constraints institutionally as state governments. And so we think our simple framework of how we think about forecast incorporation can help us understand decision-making at other large organizations as well, in addition to state governments, such as institutional investors, corporations, and agencies. Thank you so much. I look forward to more comments.
Can you remind me of the units of the Bauer-Swanson shock? Is this like a 1 standard deviation shock?
So it is, so you take it's like we think about it as a short-term shock. So you take like the first 4 quarters of euro dollar futures and you take the 30-minute change in these around the FOMC
Yeah.
announcements, and you take the first principal component and you standardize it so that it's the same units as like the fourth quarter euro dollar future.
So it's a 1 percentage point.
So
change.
honestly, the magnitude of the surprise, especially because when you use the residualized version, you residualize it with a bunch of macro variables to take out the predictable component. The magnitude of that itself is not very intuitive, which is why we compare it by running the same regression with GDP on the left-hand side. So we instead compare those coefficients, which is a little bit more intuitive. That
Any other
helps.
questions?
You mentioned you had the line items to the budget.
Yes.
I was curious, are there certain subcomponents of the budget that are more sensitive to each
Yes.
where you can kind of point out that it's a specific sub?
Great. Yes. So we spent a lot of time using LLMs and manual checking to categorize the various state line items because they really vary across states. So we did two things. One is looking at the budget stage. If you change your revenue expectations during the budgeting stage, what do you change in terms of expenditures? Up and down, basically. There's not too much asymmetry here, and you can see sort of the effects are not that different across categories. The differences are more interesting in the execution stage. So if you have a shortfall in revenues relative to your expectations during the fiscal year, or you have a windfall in green, what do you cut or add in terms of spending? So it looks like infrastructure and general government, which is maybe just like a slush fund, is what is increased if there is a revenue windfall. Infrastructure here, I should say, is things like maintenance capex. It's not actual capital spending, which is isn't a separate budget. And education is the thing that's cut the most. Yeah. Yes, Courtney.
I was surprised with the monetary policy shock. They like meetings occur roughly every 2 weeks. We expect maybe those to be a bit shorter and maybe shifted. So frequently.
Oh, yeah, that's a great point. So we do a few robustness checks in the paper to see if it's driven just by December effects, and it's not. But I think, yeah, there's probably more we can do to try to understand that in terms of like the different kinds of shocks. Yeah.
I think that this is a treatment should integrate to, because you're always comparing one state that hasn't been the winter to one that's not been the winter. I guess the other state will incorporate budget somewhere.
Yes.
Somewhat the shots showed up to zero.
Right. Yes. And at the state spending side, they do. But what's interesting is the effect on the firms is actually kind of persistent because of those adjustment costs that firms face.
Staggered treatment design that integrate. Exactly, you're documenting it.
Yes. Yep.
Not setting what you're estimating is. I don't understand what it is. Very complicated things. But I think it's worth looking at that literature because they have specific estimated consequences.
Perfect. Okay. Thank you for that suggestion.
There's a version by Oxford, Florida, and co-authors that make it easy for you to implement without having it's basically a heterogeneous treatment and you're getting timing.
Perfect. Okay. Thank you, Valerie.
Okay, I think we should move on to the next paper. Thank you very much.
Okay, thanks very much for having me on the program. I'm Adam McCloskey. This is co-authored work with Alessandro Cassini and 2 grad students at Rome, Luca Rolla and Raimondo Palla. So this paper is about basically using IVs in time series settings and different things we can use about the time series settings to try to improve some of the problems with IVs. So local average treatment effects are, when you allow heterogeneity, what IVs typically estimate, since we've learned that since the early 90s. So I'm going to focus on a particular IV application in this paper, but more generally, I just want you to think about IV regression models. You can think about structural VARs identified with instruments, and I'm going to focus mostly on today on heteroscedasticity-based identification, which can be recast as instrumental variables problem. That's not new. It's not our contribution. So since, I guess, 1994, it's been known in microeconometrics that instrumental variables identify local average treatment effects. So these are average treatment effects for a subpopulation of what we'll call compliers. Those units that are moved by the instrument that are actually changing treatment status due to the instrument. So I'm gonna put this in a macro example in a little bit. So these are just generic challenges of using instrumental variables, not specific to time series right here. When you have heterogeneous treatment effects, we know that we're recovering some sort of weighted average of causal effects for compliers. You might want to know who are the compliers? What is a complier in your sample? That's typically difficult. We can use the time series setting to try to figure that out a little bit. That's one of the things we do in this paper. You might want to know whether the exclusion restriction is valid in your setting, of course, whether the instrument directly affects the outcome or only through treatment. And then finally, my favorite weak identification type of problems, trying to do inference that's identification robust, whether the instrument is strong or not, or weak or irrelevant. So it turns out that the time series can actually be helpful here, which is often not the case. Usually it makes things more complicated. Okay, so here's the example I'm going to carry through the talk, heteroscedasticity-based identification of monetary policy. I think Rigabon 2003 might be the sort of seminal reference here, and we're going to carry through an application to Emmy and John's work in 2018 of monetary policy. So I'm going to try to make things a little more specific so you can understand all this sort of technical stuff. So for example, if you're trying to use heteroscedasticity-based identification, an outcome variable could be a one-day change in asset prices. I think in the particular application we're going to use, it will be a change in forward rates. The treatment variable could be a change in short-term interest rates. Okay, so that's going to kind of be what I'm going to carry through. And the instrument here is FOMC announcement dates, just an indicator for whether or not there was an FOMC announcement. So the identification argument, this is not our paper, of course, and you're probably all familiar with this. Volatility of the shocks to the treatment variable are larger on these policy dates when you have FOMC announcements than not, while the volatility of the other shocks to the system remains constant. Okay, so that's how heteroscedasticity-based identification works. I'm going to recast it in terms of instruments in a little bit, so we can kind of get it all under one roof. But in this case, a complier here is going to be a date, a time period, or a day really, in which volatility actually increases due to an FOMC announcement. So the volatility here being volatility to short-term interest rates. So the estimand only recovers causal effects for these dates, or a weighted average really of heterogeneous causal effects for these dates, the dates for which volatility actually increased due to an FOMC announcement occurring. So you can think of it as observations for which the policy intervention is effective, if you want. Okay, so I'm going to give you sort of a verbal summary of what we do, and then I'll get a little bit more technical later. The subpopulation of compliers is unobserved because it's based on off of a counterfactual. You can't see, if you're at an FOMC date, you can't see what would have happened had you not been at that FOMC date. You can't see what would have happened to volatility in that counterfactual world. So even when local average treatment effect is strongly identified, say you have a strong instrument, which we don't always, the observations it represents are not known. This is the weighted average of compliers. You don't know what the compliers are, so you don't necessarily know what you're really estimating in this heterogeneous treatment effects world. So identification of compliers can be important for many reasons, and we're going to try to convince you that we do identify compliers. For example, which units does the policy, like the FOMC announcement, actually affect? do they correspond to things we care about, economically or politically relevant groups or time periods? You might want to assess time variation in how much the instrument actually affects the treatment. And this will be interesting for external validity. If you're estimating via IV or heteroscedasticity-based identification, you might want to know what types of dates your estimate's actually representing causal effects for. Okay, so this is just motivation. We show how to identify the subpopulation of compliers using the sort of a smoothness structure of the time series data. You can think of it as local stationarity. So we assume the mean potential treatment assignments, which I'll give a formal definition for, at fixed instrument values. So here the instrument's just going to indicate whether there's an FOMC announcement or not, are going to vary smoothly over time. So the average, whether or not volatility would increase at an FOMC date or not, it can be non-stationary. So this average could vary over time, but smoothly over time, sort of a continuity argument here. So using this assumption, we're going to make like local comparisons of observed treatments at different instrument values. So nearby, this will become much more clear later, in order to identify whether a given time period is a complier or a non-complier. Okay, so whether or not it would have, I guess if we're at an FOMC date, whether or not in the counterfactual world you would have gotten a smaller amount of interest rate volatility at that particular date, for example. Okay, and then piggybacking off of this result, once we can identify compliers, it allows us to test the exclusion restriction. So it allows us to test whether the instrument directly affects the outcome variable, not just through the treatment. When we add another assumption, which is ruling out in the sort of microeconometrics language, what are called defiers. So a defier in this setting would be a time period at which you would actually get lower volatility due to an FOMC announcement. So once we rule this out, we can actually identify the non-compliers and the compliers and use the non-complier subpopulation to test the exclusion restriction, because we know the non-compliers their treatment is not responding to the instrument. So then we can see whether their outcome responds to the instrument in order to test the exclusion restriction. That's the basic story there. Okay, so here's a bunch of notation, sorry. I have to introduce some of this potential outcomes framework here. So Y is the outcome of interest, D is the treatment of interest, Z is the instrument. We're going to think about sort of counterfactual paths of both the outcome and the treatment. So YT plus H, at time T plus H, along this path, the lowercase is going to be counterfactuals. Along this path of treatment and instrument, this is going to be the value of the outcome. So it's a counterfactual value of the outcome under these sort of hypothetical or counterfactual sequences. And then some more notation. When we look at YT comma H, that's only the counterfactual as if we only change the treatment and instrument at time T, okay? Leaving everything else as occurs in the data. That's what this notation means. So uppercase D is the actual occurrence in the data. Lowercase are counterfactual values here. Okay, so the observed outcome, of course, then is going to be, if you insert for these counterfactual values, the actual values, this is what you would observe in the data. Okay, just trying to get the notation clear. And then finally, we have the counterfactual treatment at a particular instrument value. So you can think of this as, well, this is going to end up being interest rate volatility at FOMC versus non-FOMC dates, but counterfactuals. Okay, now that I have all this notation in mind, I'm going to introduce some very sort of standard assumptions in the microeconometrics literature, but I'm going to try to extend them a bit to a time series setting to make them a bit more palatable. So the first one is instrument independence. The instrument is independent of these counterfactual outcomes and counterfactual treatment values. Conditional now on this VT variable. So VT can contain past histories if you're worried about serial dependence. It can contain covariates and things of that nature. But once we condition on these VT values, we're assuming the instrument is independent of these potential outcomes and potential treatment variables, as they're called in microeconometrics. So in the example, it's potential asset prices and interest rates are independent of whether an FOMC announcement occurs. So remember, this is potential, not actual. The exclusion restriction, which you need to get anywhere using an IV, is that potential outcomes don't depend directly on the value of the instrument, right? So once you fix the treatment variable, the counterfactual treatment D, the probability that the outcome differs along different instruments at the same treatment variable is, or I'm sorry, the probability differs is 0, the probability it's the same is 1. Okay, so in this case, it would be that you get the same response of potential asset prices, whether there's an FOMC announcement or not. This is what we're interested in testing, because we need that in order to actually interpret the IVS demand as late. And then finally, this is just new notation. S0T is going to be the subpopulation for which we'll say the IV regression has a first stage, if you want. So it's the subpopulation for which the expected value of the potential treatment is actually a function of the instrument, and not so the instrument will, on average, actually change the treatment. Okay, so I think that's probably good there. So the first thing I'm going to look at is the whole suite of things. Yeah, go ahead, Leila.
So, question on this IT column.
Yeah.
You fix intervene IT and little b and little b, but keep all the future operations. So from a structural perspective, this is kind of weird because you're assuming that its intervention will not affect the future. And so, for example, if y dt follows a y, so then once you intervene dt and little d, then all of the future observations will change.
This is just notation. There's no assumption here. I'm not saying that. So this is still a random variable. So it's not like this is now deterministic now that I've pinned down little d and little z. It's just shorthand for allowing for, this stuff is still affecting. The future is still affecting. It's just shorthand notation for just saying, I'm only going to look at counterfactuals at time t and time z.
Are you, say, capital D equals 1 function little d?
Sorry, say that again.
So like, if the volatility changes
Yeah.
at time t, are you going to assume that volatility will be a function of the change? Okay. So in other words, here, shall I view this as a function of little d in terms of just changes day t, or should I also propagate this little d to the future and then treat the sort of combo effect as the counterpart?
So so if you want to look at like fixing the entire sequence, it's this notation. If you only want to fix just one intervening thing, it's this notation, but it doesn't mean that this no longer affects the future values of y. Yeah, it's just pure notation. Yeah. Okay, so the first thing we're going to look at is a sort of standard thing when you're looking at instruments. It's an IV, or it's a walled estimand. So here, what you're seeing is, oops. Okay, so this is an estimand. The difference in conditional outcomes at different instrument values, fixing, of course, the V's, those are kind of hidden in the background, divided by the difference in treatment values at the different instrument values. So this is a well-defined estimand for observations that have a first stage. Otherwise, the denominator can be 0. So this is just an estimand. What I'm going to show you is that, okay, so you can estimate this estimand directly from data. And in fact, this will map into heteroscedasticity-based identification on the next slide. Once we introduce a monotonicity assumption, we can interpret this estimand in terms of a weighted average of causal effects here. Okay, so monotonicity, we can say without loss, the potential treatment is increasing, say, in the instrument. You can make it decreasing also, but this is, we'll just say it's increasing. And a complier is going to be a time period for which the potential treatment is strictly increasing. So think of you're getting treatment if and only if you were assigned treatment, sort of in the micro setting. But in this setting, these are days where the volatility of interest rates is going to be higher if and only if there's an FOMC announcement. Okay, so the reason I'm introducing compliers is because the sort of first small result here is the walled estimand recovers a weighted average treatment effects for compliers. It's a little bit hard to read if you're not used to this notation, but so here's your marginal. So if you're looking at T plus H, we're usually going to make H 0, but this is the marginal treatment effect at time period T plus H when you perturb the treatment, but this is the expected value of it given you're a complier. Okay, so it's a little hard to read, but that's the conditioning statement here. And then these are weights on different complier values. Okay, they integrate to 1 and they're positive under these assumptions. So you need monotonicity. I think Christian mentioned the monotonicity assumption. You need monotonicity for this interpretation, this sort of, you're looking at a convex combination of average treatment effects. What else? The exclusion restriction is needed for this, and the independence condition is needed for this as well. Okay, so when this isn't actually like a big new result, I'll be honest with you. What's interesting is when you apply it to heteroscedasticity-based identification, which I'm going to do here. Okay, so let me get some more notation. P is going to be the policy sample, so these are going to be the FOMC announcement dates. C is going to be the control sample. These are going to be the non-FOMC announcement dates. We're going to map them into the instruments. We're going to say Z is 1 in the policy sample and it's 0 in the control sample. Okay, so now you see there are tildes on these. Yeah.
Can I just ask the motivating question? Like in the medical applications, I sort of see why you get different treatment effects depending on whether you're a complier or not.
Yeah.
Whether you take the effect of the drug is going to be different if you're sick versus you're not sick. When we're looking at the effect of the FOMC shock on forward rates, help me understand why this technology is needed. Why is it that it's not always the same treatment effect?
I can't tell you for sure if it's, you're basically saying, why do I care about heterogeneous treatment effects in this application? I can't tell you for sure that we have heterogeneous treatment effects, but I can say that there are different time periods, like during the financial crisis, where you may expect things to respond differently, or like during COVID, you may expect things to respond differently. So that's kind of our take on why we look into this. If you don't like any of the heterogeneous stuff, we also have stuff that only holds for linearity. That's like more later in the talk. But yeah. Okay. All right. So policy sample, control sample, and these are going to just be correspond to instrument values, 0 and 1. So just a binary instrument here. You see tildes on these, right? They're not actually the same Y and D as before when we're talking about heteroscedasticity-based identification. So Y tilde here is going to be something like daily change in a forward rate, and D tilde is going to be like change in short-term interest rates or intermediate-term interest rates, for example. Okay, so this is the result from Rigabon. If we're interested in just the coefficient beta 0, so how treatment affects outcome, as I've been kind of saying it. If we have this sort of heteroscedasticity, so we have during the policy dates, we have higher variance to the treatment than during the control dates, but we have the same variance to for the shock to the outcome. This is this old result from Rigabon. You can actually identify beta 0 there through this ratio. Okay, so I'm not going to show you the algebra for it. This is not our work. But actually, if you look back, this is an empirical Waldes demand. So that's why I showed you the Waldes demand on the last slide, but it's a bit different. This is the corresponding Waldes demand. So I'm going to flip, sorry for flipping slides. The Waldes demand I showed you before had a Y here, right, and a D here. The corresponding Waldes demand for heteroscedasticity-based identification, the Y is D tilde times Y tilde. So it's interest rates times forward rates is the outcome variable you're actually dealing with here. And the D variable is the volatility of the interest rates. So if we are in a linear world, then this Waldes demand does identify the coefficient, but things get pretty funky if we're not in a homogeneous treatment effect world. So if you apply that previous result that I showed you, what the Waldes demand recovers in terms of weighted average treatment effects, this is what you get for heteroscedasticity-based identification. So if you look inside of here, we're still looking at compliers. We're still conditioning on compliers, but now we're looking at the marginal effect of short-term interest rates times forward rates as an effect for short-term interest rate volatility. So it's a little, I'm pointing out, this is a bit hard to interpret and maybe not what you're after if you have heterogeneous treatment effects. But if you believe that you're at least approximately linear or that you do have homogeneous linear model, then this just recovers the coefficient you're interested in. But it's a bit fragile in terms of heterogeneous treatment effects. That's the only thing I really wanted to point out here. Okay. Okay, so now I'm gonna, any questions? No. I'm gonna talk about compliers and identifying compliers. So for now, we're going to assume the treatment is binary. The paper, generalizes this. T is a complier, so a time period is a complier. If, here this is volatility. Remember, this is d tilde squared. Volatility is higher at the instrument value of 1 than 0, almost surely. Okay, so you're getting higher volatility on FOMC announcement dates. The identification problem to figure out whether any given time period is a complier is you don't observe both dt of 0 and dt of 1, you only observe one of them. So on FOMC announcement dates, we observe dt of 1 and vice versa, right? So we're putting this assumption down, deterministic complier status. Each time period is either a complier with probability 1 or not. We show this small result that the probability that time period t is a complier is equivalent to the expected value of its treatment under an instrument of 1 is bigger than its expected value of a treatment under 0. This is just a step in order to identify compliers here. So this is yet another assumption here, this deterministic complier status. Okay, so this is how we identify compliers. It's pretty simple. Take time period t0. Let's say this is an FOMC announcement date. This argument works if it's not also. What we're going to do is assume something like local stationarity. Assume, at least as the sample gets big, that the expected counterfactual treatment status at any instrument value is continuous as you move along time. So when you map this into the unit interval, your sample into the unit interval using sort of local asymptotics, the expected value of the treatment at any given instrument value is very smoothly, it's continuous. So this continuity is going to allow us to look at local means around t0 to try to figure out if this is an FOMC announcement date, what would have the value of dt have been if it were not an FOMC announcement date. So what we're going to do is look around at the days nearby, okay? Because this is continuous, we can then prove that if we look at local means, these are just bins around the date, we're going to get the counterfactual at dt of 0, the average counterfactual, the expected value of dt of 0. So that's, yeah, so averaging at ds values in the control sample, not at the policy sample, but nearby that policy date. You can just look at means, or you can look at kernel-based means that sort of downweight further away from t0. But we show under these conditions, this local stationarity condition, that the average local mean at policy dates nearby minus the average local mean at control dates nearby are going to converge to some positive value if it's a complier, if date t is a complier. And so then you can, of course, if you're looking at means, do t-tests under central limit theorem assumptions and tests for compliance. Yeah.
So if you thought that the dominant source of other variation was, I don't know, other announcements or like the day of the week effects of some form,
yeah,
then would you want to do the local thing in some other way?
Yeah, you want to be careful about how you do the local thing. You want to make sure that, yes. So if you're worried about other stuff like volatility being different on different days of the week, you definitely want to be averaging at like the same day of the week. Yes. Yeah. So,
following up something a little earlier, would you thinking about doing a one-sided kernel here rather than two-sided? Like FOMC announcement happens, volatility spikes, it remained elevated for a while. It would seem you'd want to use just the pre-FOMC days to get your locals.
yeah, that could be the case. Yeah, this is I mean, under different assumptions, you're going to want different types of kernels in one-sided versus two-sided. Yeah. Yeah, this is under the assumption that volatility would just increase on the FOMC date and not remain persistent. Yeah, yeah. Okay. Okay, so using these sort of local means comparisons, we can get an estimate of the complier group And then the non-complier group is going to be everything else. Okay, so this can be applied, of course, beyond FOMC announcements. Oh, wait, actually, before I get to that, let me show you what this looks like in data. Okay, so we're actually going to do this one-sided t-testing for compliance in this application. So remember, D is this D tilde squared. The null hypothesis is a particular data is a non-complier. The alternative is it's a complier. This is a one-sided alternative because this local means comparison is going to be positive in the limit. So here we kind of divided up the control and policy samples. So these are FOMC dates. These are non-FOMC dates from, let's see, 04 to 2013. I am colorblind, so is this darker shade is non-compliers and the lighter shade are compliers. You macroeconomists might have some interpretation why there might have been more non-compliance following the financial crisis. I've heard it might be from a lack of forward guidance, but I'm not going to give you guys a great amount of interpretation here. But this is what we got from the data from this one-sided t-test at a 10% level. So yeah, non-compliance occurred primarily following the financial crisis. This is like during the zero lower bound period, and it's sort of sporadically leading up to the financial crisis in this sort of test. Okay. Now, using the identification of compliers to test the exclusion restriction. So the exclusion restriction holds when you have a binary instrument. Very simply, if I look at a counterfactual value of the treatment, fix it at D, the probability that the outcome at the instrument of 1 and 0 is the outcomes are equal, whether you're at an FOMC announcement or not. So this is the little trick here. If we know who the non-compliers are, we can test this pretty directly. We have to rule out defiers for this to work. So you can't have, a date's going to have higher volatility because there's or when there's an FOMC announcement. This will not work then. So we're ruling out defiers. That makes the non-complier group just the group of time periods that don't respond to the instrument, or volatility that's not different due to an FOMC announcement date. And we're going to take the intersection of these non-complier groups with the policy dates and with the control dates, called that NCP and NCC. Let me check time. Okay, better hurry up. Okay, so the exclusion restriction would then imply that the average outcome for a non-complier at policy dates would be the same as at control dates, because the non-compliers are not, their treatment status doesn't respond to the instrument. And if the exclusion restriction holds, their outcome should therefore not respond to the instrument as well. Yeah. So we're going to basically just test this using, again, a local means comparison. You can do fancier stuff using kernels or downweighting or whatever. So under the assumptions I've given you, we show the exclusion restriction holds if the mean outcomes in this non-compliance policy group is the same asymptotically as the mean outcomes in the non-compliance control group. And again, you can test this using, these are sample means. You can use a t-test for the exclusion restriction here, and we do. And in the application, this heteroscedasticity-based identification application, we find the exclusion restriction holds. I don't know how you would say this, strongly don't reject the null. We get very small t statistics. So we fail to reject the exclusion restriction. Therefore, we conclude that yes, the exclusion restriction holds in this particular application, probably. Okay. Yeah.
So just to give feedback on the interpretation of the post-financial crisis thing, I think the right way to describe this is probably just there was a lot of forward guidance and people knew that interest rates are going to stay at 0. So
volatility didn't change. Yeah. Yeah. Okay. Yeah. Yeah. Okay. Thank you. Yeah. Okay. I don't know. The before one is a bit harder to interpret. Yeah, I don't know. Okay. Thank you. Yeah.
I think one so not a good competition, but one and perhaps downside of this particular application of these ideas is that often when you don't know who the compliers are, it's because there are always takers and never takers. There's some combination of them, and that makes the world very complicated. But in this setting, I think you have no always takers. It's never the case that you would have a spike, in the alternative world where if there had not been an FOMC day on that particular day, what you have is never takers. You have dates where there's no news on the FOMC day.
Yeah.
But that's kind of a simple world where it's easy to figure out who the compliers are. So if anything happens on those dates, it's a complier. So
a never taker is one where volatility is low, right?
yeah, but a never taker is like whether or not there's an FOMC date, nothing happens on
Right.
that day.
Yeah.
Right. And there are plenty of those days. You know, those are days where FOMC days just don't produce
Right.
any monetary
Yeah.
news.
Yeah, that's like these.
That's like those.
But these ones I think are the opposite. You get high volatility.
It's very hard to think of like an always taper in the setting. So anyway,
Yeah, okay.
that's something to think
Okay, fair enough. But I think this might be the opposite. All right. Okay, great. So now I'm going to get into identification. Oh wait, no, I'm going to get into how to try to increase identifying power in these type of settings with time series. So local average treatment effects, or even, you know, if you're in the homogeneous world, if you don't care about heterogeneity, you use IVs, you often have weak identification. That leads to problems with standard confidence intervals. I think we all kind of know this. So this is a sort of workhorse model we're going to use back to the linear world. Outcome, treatment, I guess these should have been V's, but these are, you know, exogenous covariates. The treatment, this is the model we're going to use. It depends on the instrument, but only in the subpopulation with the first stage. So that's an indicator function. So there are going to be certain time periods for which an FOMC announcement makes no difference to interest rate volatility, for example. Okay. So the first thing we're going to do is just test whether we have complete identification failure in this sort of linear setup. So whether theta is 0 or whether there is identification, but only up for certain time periods in S0T. So we developed a new first stage F statistic, basically. And we didn't work out like a rule of thumb for testing for strong identification. All we're doing is testing for a complete identification failure here. I'll call it F star. I won't show you the formula for it, but it searches over a bunch of subpopulations using a dynamic programming algorithm. And I'm just going to show you this next slide because it's using our F star statistic that searches, you know, it's searching for maximal identification strength across the subsample. So these are histograms of 1,500 specifications. Some are just, so these are time series on the top and their panel on the bottom. These are just the regular old first stage F statistics. It's a histogram of them, along with the, what is it, one, you know, the 95th and 99th quantile, or the 1 in 5% critical values for testing whether you have complete identification failure. They're just there to kind of compare the mass of the histogram at. On the right side here are the F statistics that search for the strongest identification strength, our F star statistics. So the only reason I'm showing this is to try to provide some evidence that you might gain identification by looking at subsamples in time series. The mass is a bit, you know, has a fatter right tail. You can't really compare the left to the right because they're different statistics, and you have to take into account that you're searching across subpopulations on the right. That's why you have these different critical value lines. But you can sort of heuristically see you might gain identification strength by not looking over your full sample, but looking over subsamples. This is just a heuristic argument here to try to motivate what we're doing. You can also look in the heteroscedasticity example, we can look at our F star statistic and compare it to critical values. I think I'm kind of running low on time. You can really ratchet up what looks like the identifying power by only looking over subsamples of maximal size 90, 80, and 70%, et cetera. So, you know, this is the regular first stage F statistic and the critical values under complete identification failure. And then when you're searching over the subsamples, they get quite a bit bigger. But again, you're not looking at the same distribution. These are the quantiles when you're doing a search. But you can still see they're kind of separating quite a bit from their critical values. So it may be fruitful to only look over subsamples to gain identifying power. Okay, so that's what we're going to do. So first I have an estimation procedure. You can estimate the subsamples with the highest identification strength using a standard sort of OLS criterion. I think I'm going to kind of go fast on this one because I want to do weak identification, robust inference. But you can estimate the subsamples. This nasty character here is the set of subsamples you can look over. They need to have non-negligible size. So they can't be like tiny subsamples. You can only look over a finite number of regimes within these subsamples. That's what's buried in this notation. But we have an algorithm that searches over subsamples. If you'd also like to include the second stage, so this is minimizing the sum of squared residuals over the first stage. You can also look at the reduced form for the second stage when you plug the first stage into the second stage to gain efficiency here using an FGLS criterion. But that's all I'll say. We prove consistency of the estimator of the subsample in this sort of setting when theta is not 0. Okay, so yeah, I'm gonna sort of skip to this slide. Okay, so here's back to the heteroscedasticity-based identification example. The top two, what it's called, like panels, are for the full sample. So when you estimate using the full sample of data, you're not trying to find the subsample that gives you the strongest identification power. This is for nominal and real outcome variables. This is just actually old stuff. Two-stage least squares gives you this when you run a regression. Or when you use heteroscedasticity-based identification, these are the estimates of the sort of causal effects of the short-term interest rates on the forward rates, whether they're nominal or real. Okay, so this is a standard confidence interval. This GMM block corresponds to Daniel Lewis's restat paper. I think it's a 2022 paper where he showed you can actually get over-identification using a heteroscedasticity-based identification model, and he provides a different way to estimate the beta coefficient using GMM. These are the point estimates using the same data using those that GMM condition. And these are the standard confidence intervals, and he also has identification robust confidence intervals, which are below them. What I want to point out just in the full sample is you get vastly different point estimates when you're using GMM versus two-stage least squares. Now, this could be due to heterogeneity. It could be due to weak identification. We think it's likely due to weak identification. These things are totally different, right? I mean, you get a sign flip here when you use GMM to estimate off the same data. When you use our procedure that tries to isolate the most strongly identified subsample and apply two-stage least squares and GMM using Lewis's conditions, you get estimates that are quite, well, they're not exactly the same, but they're closer, and they're all positive and significant. Yeah, I mean.
Oh, I got confused. The dependent variable was the 2-year yield, but the shock is all this short-term.
Yes. And
I was going to say that some papers also consider shocks that are longer-term interest rates, and then you might get more of this actually always linked stuff.
Okay.
Shocks to term premium.
Yeah. So maybe we should look at that long term. Okay. All right, am I out? Oh yeah.
Just a quick question. Are the estimates now the same in these two?
The estimands under heterogeneity, that's a great question. We did not analyze what the estimand is under GMM. That's exactly why I can't tell you for sure this is due to weak identification or the estimands are different under the different moment conditions. Yeah, I don't know. Yeah, good question. Okay. Okay, so finally, the last piece of like this, a lot of stuff on late or on IV and time series settings is, my sort of bread and butter is identification robust testing here. So back to the model I showed you before. This is nothing new, so no more new notation. We would like to test in this two-stage model, allowing for time varying instrument relevance, right? That's what this indicator function is all about. We just like to test your standard, what is beta equal to 0 or whatever, right? Beta is equal to beta naught, two-sided testing of the parameter that, maps the treatment into the outcome variable. So here's an observation we made at first. You can, of course, use some really good identification robust tests here, the Anderson-Rubin Lagrange multiplier or the conditional likelihood ratio test. You can use it in this setting, but you probably shouldn't use it directly off of the shelf. And here's why. If you work through some of the statistical arguments, especially in Moreira's CLR paper, if you just use the entire vector Z across all of the time periods as your instrument, it's not efficient. And the way, technically the reason why it's not efficient is that it's a function of a statistic that's not a sufficient statistic for the parameters in this model. Okay, so that's just a technicality. We modify it, if you know what the subpopulation S0T is, to be only a function of sufficient statistics for beta and theta. And in fact, you can just view it as, don't use Z as the instrument, use Z interacted with the indicator as the instrument, which is more or less kind of obvious. That gains you, it gets you back to efficiency. Okay, but this is for a known subpopulation. When you know where the first stage exists, you don't typically know that. You usually have to estimate. I just showed you we have a way of estimating it. This is the more interesting one for me. You don't know the subpopulation in which you have a first stage, in which the FOMC announcement actually affects volatility. So here this is the same old equation, but I don't know what S0 is. I don't know what that subpopulation is. Now, again, we show the standard statistics are not efficient. The standard weak identification robust statistics are not efficient because they are based off of statistics that are not sufficient for beta and theta, but we modify them now. Actually, we figure out what the empirical process is that is a sufficient statistic for beta and theta here. So it's actually a full empirical process, not a single statistic. And I'm not showing you the math, but we have modified versions of the AR, LM, and CLR statistic that are functions of this sufficient empirical process, and they get you a lot of power gains in identification robust testing, which is this graph here. So the blue is us. These are our power curves for the CLR and LM, which coincide here because you have one instrument. And then this is the power, whatever color this is the power of the standard CLR and LM statistic. And then there's also a nice paper by, I think it's 2013, by Magnuson and Mavroedis that also tries to use time-varying identification strength and identification robust statistics. So that's what the other black lines are. But you can see the power is much higher. This is for a theta that is local to 0. So it's a weak identification setting. You're weakly identified over subsamples and non-identified over other subsamples. So you get a lot of power gains from doing these modified statistics. Oh, there's a clock right here. And then if you apply it, if you apply this identification robust testing to the application that I've been talking about throughout, we get a lot more rejections. So LM, CLR, these are the standard statistics here that just use the full sample, and then LM of S hat and CLR of S hat, these are our new statistics that implicitly estimate the subpopulation. The checks are rejection of the null of 0, the X's are non-rejection. You get a lot more rejections is what this is mostly about, which you would kind of expect from the power plots. Yeah, okay. I think I'm pretty close to being out of time, so let me wrap it. This is a whole suite to analyze IVS demands in a time series setting, so allowing for heterogeneity. We apply it to heteroscedasticity-based identification, show how to identify compliers, how to test the exclusion restriction, how to try to find the most strongly identified subsample, and do identification robust inference. And thank you for listening.
Time for a question or two.
Cool. Thanks.
Okay, if not,